Hello everyone, and welcome to another session of our full stack practical deep learning course. In the previous section, we learned that when we have a machine learning model, we are able to train this model by passing in inputs and outputs, such that after the model has been trained, this model is able to take in an input like this image right here and say confidently that this image contains a damaged car. Now, these inputs and outputs usually are multi-dimensional arrays called tensors. In this section, we'll look at the basics of TensorFlow tensors, casting and tensors, tensor initialization, tensor indexing, broadcasting tensors, algebraic operations with tensors, matrix operations with tensors, commonly used functions in machine learning, ranked tensors, sparse tensors, and finally string tensors. Don't forget to subscribe to this channel and hit that notification button so you don't miss amazing content like this. Without wasting any more of your time, let's get into TensorFlow tensors. Tensors could be seen as multi-dimensional arrays, where an array itself is an ordered arrangement of numbers. These keywords, numbers, ordered, arrays, and multi-dimensional are very important, as many times the data we have at hand could be represented using numbers and stored in arrays, where these arrays could be multi-dimensional. In this particular case, we have a two-dimensional array. So here we have the first dimension and the second dimension. It should be noted that sometimes tensors could be of zero dimension. That is in the case where we have only one element. So this tensor, for example, is a zero dimension tensor. Now, if we take this other example right here, we have a one-dimensional tensor. Here we have this vector array containing numbers which we've stacked up in just one dimension. Now, let's take another example. We could have this, say 2, -3, 5, 6, 8, and say 12. So we could have this one-dimensional tensor right here. So here we have 0 dimension, here we have 1 dimension, and now we have this matrix, which is a 2D array right here. Now we could also call this a 2D tensor. So this is 0-dimensional tensor, 1-dimensional tensor, 2-dimensional tensor, or a matrix, which is a more common way of calling 2D arrays. So if you look carefully, you will notice a certain pattern as we go from 0D to 1D up to 2D. In order to get a 1D array, we stack up several 0D arrays. And in order to get a 2D array or 2D tensor, we stack up several 1D tensors. Notice how we could take this 2, 0, -3 and then fit it right here. And then take this again, fit it right here. So here we have another 1D, another 1D, and finally this other 1D. Now all these form a 2D tensor. From this point, building a 3-dimensional tensor becomes evident. Looking at this carefully, we'll notice that here we have this 1D tensor, this 1D tensor, which have both been stacked up to form a 2D tensor. So we have this 2D tensor stacked up with this 2D tensor right here, another 2D tensor, another 2D tensor, and now all these form a three-dimensional tensor. Also, before going any further, note that tensors have what we call a shape. Now let's look at how we get this. For the one-dimensional tensor right here, it has a shape of 3. Now for this two-dimensional tensor, we have a shape of 4 by 3. Now let's get to understand how we get this. Here we have 3, so we could write this as 3 like this. So there we go, we have the shape 3. Here we have shape 4 by 3, and this is because we have 4 rows. So notice we have 1, 2, 3, 4 rows, and we have 3 columns. Notice we have 1, 2, 3 columns, and here just 3 because we had 1, 2, 3 columns. Since here we had dealing with a 1D tensor, we have just one value right here. Here 2D tensor, we have 1, 2 values. So here's our first dimension and the second dimension. So we have number of rows equals 4 and number of columns equals 3. Getting to the 3D tensor, the way we look at this is we start by counting the number of 2D tensors we have. So here we have 1, 2, 3, and 4. So we have 4 2D tensors, and each and every one of these ordered arrays or ordered 2D tensors we have in here have 1 row 2. So we have 1, 2 rows here. See 1, 2, 1, 2, needless counting because all this will always give you 2 rows. So we're supposing that we have 4 2D arrays, and for each and every 2D array we have 2 rows and, you guessed it right, 3 columns. So we have 1, 2, 1, 2, 3. So here we have 1, 2, 3, 4, and 1, 2, and 1, 2, 3. So we have 4 by 2 by 3 as the shape of this three-dimensional array we have right here. So notice we have 1, 2, 3 elements. Another way, or another better way of writing out this 3D array we have here is having this. So we see that we have this first 2D array, here is it. This next 2D array, here is it. This next, here is it. And finally this, here we go. At this point, we could now get to see how this type of tensors are built with TensorFlow. So all we need to do, since we're dealing with collab, is to import TensorFlow as TF. Now, once we have this TensorFlow imported, we simply run the cell. So that's it. We're supposing we have some basic knowledge on Python programming, so you should understand this syntax right here. We will then go straight away into creating our first tensor. We call it tensor 0D. This is tensor 0D equals, and look carefully the syntax. We have tf.constant, and then you put in this tensor right here. So we have, you see, you put in constant, the value, you could specify the data type, the shape, and then the name. So we'll look at this shortly. So here we go, we have this. We could simply run this cell again. A shortcut is by doing the shift enter. So do shift enter, and we have that. So that's it. So there we go, we have this tensor, and we could print out this value. Let's just print out this value in here. We have print tensor 0D. We'll run that, and there we go, we have this tensor which has been created with value 1, shape, you see 0 dimensional, so we find this empty brackets right here, and then the D type is int 32. So it's an integer of precision 32. And that's how easy it is to create TensorFlow tensors. So let's now look at a 1D tensor. So we'll take that off. We have here one dimensional. We'll specify this. So we'll take out the same values here. So we have this list 2, 0, -3, and then we have right here 1D. So let's run that and see what we get. We find that we have this one-dimensional tensor right here, or rather this 1D list, which is a value in this one-dimensional tensor. We have this Python list, which we have specified right here, this one-dimensional list, and we have the shape with the D type int 32. From this point, it becomes evident that our next move will be to go to the two-dimensional tensor. So again, we copy this, we have that, and we replicate what we got from this. So instead of having 2, 0, -3 like this, we're gonna have 1, 2, 0. So yeah, we have, first of all, since we have a 2D array, we have to add this other square bracket right here. So we have this square bracket. We could put, let's first start by putting like this, where we have 1, 2, 0. There we go. So that's the first. So because we recall that we're stacking up 1D arrays or 1D tensors. So we have this 1D tensor which we stack up. We go to the next, we add another 1D tensor. In this case, it's 3, 5, -1. So we have that 3, 5, -1. And then we move to the next. We have 1, 5, 6, 1, 5, 6. Again to the next, we have 2, 3, 8, 2. And then from here, we close the square bracket which we had opened right here. Because for this, we open up the square bracket and close it for this 1D tensor. Next, 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 and then finally we have to close up this one right here. So we could have it like this. Let's have that, then take this up. So there we go, we've opened it and then closed it right here. For this, just put it, there we go. So that's it, we've created our 2D tensor. So yeah, we'll print this out, 2D, and here is the response we get, just exactly what we gotten already. That is a shape of 4 by 3. Again, we move now to the 3-dimensional tensor. So we copy this again. We have that. Scroll a bit. So there we go. We have this 3D tensor we want to build. We'll start by building the 2D tensors. Here we have 1, 2, 0, 3, 5, -1. So we have 35, 1, 2, 0, 3, 5, -1. Take this off. There we go. So first of all, we have this 2D tensor right here. Let's do this. So we have this 2D tensor. There we go. There's it here. And then put that comma. And then we're gonna build again another 2D tensor. The next is 10, 2, 0, 1, 0, 2. So let's copy this. Put it right here. So there we go. We have 10, 2, 0 and 1, 0, 2. 1, 0, 2. There we have 1. There we go. So this is the next 2D tensor. Next one. Copy that again. See, we have 5, 8, 0. So here we have 5, 8, 0, 2, 7, 0, 2, 7, and 0. Finally, we have this last one. So let's copy this. Finally, we have this last one, 2, 1, 9. So here we have 2, 1, 9, and 4, -3, 32. -3, 4. Okay, so we've built this 4 different 2D tensors. We have 1, 2, 3, and 4. Be careful with these commas right here, because this separates the different 2D tensors which we're stacking up to form the 3D tensor. Let's put it this way. Let's have this, let's have this, and finally we're gonna have this. Okay, so there we go, we have this 4 2D tensors, and then finally we could close up this bracket which we opened up here, the square bracket which we opened up. So let's have that, and there we go. So let's take this from here. Okay, so we've opened up here and then we've closed it up this way. For this we have it this way. So this is our 2D tensor, or rather this is our 3D tensor, because here we've had a 2D tensor and now we're moving to 3D. So we have our 3D tensor, 3D, and then we could run that. That's the answer we get. We have a 4, as we saw it here, by 2 by 3 shaped 3-dimensional tensor. So hope you've gotten the concept of dimensions with tensors very well. You could also get the shape by doing this. So here we go, we have the tensor dot shape. So we run that and we have just the shape this time around. We could also get endim, number of dimensions. So we have that 3. So yeah, it tells us dimension 3. Obviously this should give us, endim here should give us 2. So that's it, 2. And then we have shape, that's perfect. Take this off, and we have our tensor. We now move to one extra dimension, this time around a 4th dimension, by stacking up several 3-dimensional arrays or 3-dimensional tensors. So we have this first tensor right here, which we've seen already. We have this other tensor. So let's do this, take this off. We have this first one. We have this next one, which is gotten also by stacking up the 2D tensors. And then we have this one. So if we pick this and we try to fit it in here, we see there's it. So we have this tensor right here, and then this 387. So this is it. This is this tensor right here. We have this one 825. Look at it. This is this tensor right here. So we have this 3D tensors which have been stacked up to form a 4D tensor. Now, in creating or in looking at the shape of this 4D tensor, we'll start by counting how many 3D tensors do we have. We have 3 3D tensors, but then for each of these 3D tensors we are talking about 4 2D tensors. So we have 4 2D tensors. For each of these 4 2D tensors, that is for each and every one of these, we have 2 rows, that's 2, and 3 columns. So there we go, we've gotten the shape of this tensor, of this 4-dimensional tensor right here. We now head straight up to the code and build up this 4D tensor. So there we go again, we have 3D. Now we'll get very careful, we have this one here. So we have this 3D tensor. So let's have this 3D tensor right here again. Let's take this way. There we go, we have this 3D tensor. That's it. So there we go, we have this 3D tensor. We copy this, put the comma, and then you paste it right here. So this is this one, and then we simply modify its values. Recall that this tensor we had here is basically what we had gotten already, but for this next one it's different, so we have to rewrite that. So here we have not just 1 2 0 3 5 -1, just like with this, but now we have 0 to 5. So here we have 0 to 5, 5 3 1, 5 3 1, 0 to 0, 0 to 0, -1 10 0, -1 10 0, 0 5 1, Here we have 051, 051, 170, 170, 387, 387, 232. So to take this off, 232. So that's it. We've built up this second 3D tensor. There we go. Now the next, we put a comma, and then we'll do same. So we take this, copy that, and then paste. So let's have this. We have now this last one, 5, or rather 4, 5, 4, 3, 1, 1, 4, 5, 4, 3, 1, 1. Next 0, 2, 5, 0, 4, 3, 0, 2, 5, 0, 4, 3. Next 3, 2, 4, 5, 8, 3, 3, 2, 4, 5, 8, 3. Finally 8, 2, 5, 2, 3, 3. 8, 2, 5, 2, 3, 3, and that's it. So we've just built our third 3D tensor. Now we could, as usual, add this. So we've added this square bracket which closes that up, and then we add this one which opens it up right here. So we've opened it up and then closed it below here. So now we'll just take this up. There we go. We have our 3D, and then 3D right here, which now form a 4D tensor. So let's take this. That's it. We have here 4. So we'll change that. 4D tensor. Here is 4D. 4D tensor. We have that. Okay, so let's run this and see what we get. Number of dimensions 4. That's normal. Let's look at the shape. We get exactly the same shape we just got. And then let's now finally print out our tensor. So we have our tensor, which is this 4-dimensional tensor of shape 3 by 4 by 2 by 3 and of type int32. As you may have noticed, the default data type we've been getting so far is a int32. Now, if we add a decimal right here, let's run this again, we'll find that we also have this default float 32 d type, and you'll also see this additional decimal here which wasn't initially put in right here. So in fact, when creating this type of tensors, we could either get the int32 or the float 32 by default, and if in case we want to change this, we could simply specify the data type. So put this data type equals tf.float16. So run that, and you find that we have a different data type. Now if you put int, for example 16 here, you should have an error, and this is because in here we are not able to convert this float into an int. So kind of convert this to tensor of d type int16. So that's it. It should be noted that this extra numbers added after the data types are the precision values. So when we have a precision value of 16, as you could see here, we have int16, and a precision value of 64 would have int64. Now we have this error for obvious reasons. Let's take this to float. So if we have float 64, so we have that. In this case, our precision value is 64. The higher this precision value, the higher the amount of space allocated in storing this tensor. So this means that at a higher precision value, the stored value of the tensor by the computer looks more like the exact value of that tensor. Hence, when building machine learning models, we may want to reduce this precision value or increase its value depending on the context. In cases where we want to prioritize speed, like in low resource environments, we'll prefer to work with tensors of lower precision values, since computations could be done faster. But in cases where we want to prioritize reducing the computation errors, then we'll prefer higher precision data types. Let's take a quick look at the documentation. Now, note that the documentation contains everything you need to be an expert TensorFlow developer, so you should actually make this documentation your friend. Now, that said, we get into tf.dtypes right here. We look at the overview. We're there already even. So you just have that, and then scroll down. Yeah, you could see the different data types. Yeah, we have the quantized data types, which are in fact data types possessed by tensors, which are produced as a result of quantization. Now, you could check out the quantization documentation right here. We have this quantize method, and is the output of this method which produces such data types we just had here. So go back to this. Now let's try to understand this quantization process, which leads to the QINTXS data types, for example. Now we have this weights, which we had seen previously. That's in the previous section. We have this weights, and we suppose that during the training of our model, we were working with weights, that is these tensors which have values or which are of data type, for example, say float 32. But now we get into production. Get into production in this case means that we have built this model and we want to use this model in a chip that's in a small microprocessor, which doesn't contain very much memory and maybe doesn't contain a specialized GPU for doing fast mathematical computations. And in that case, we can't afford to have our tensors in the float 32 type. So in that case, we do what we call quantization, where we reduce the precision of this weights or the tensors, and we now have this new tensors in this data type of lower precision. And so this outputs of this quantization process are tensors of data type QINTXS. So you see here this Q which is added, signifying quantization. Then we get to the B float 16, which actually stands for brain floating point 16. And the reason why this is very important, or this data type is very important, is that it permits us leave from 16-bit to 32-bit precision very easily, and from 32-bit precision to 16-bit precision very easily too. You could check out this article on the Google Cloud website entitled "The Secret is High Performance on Cloud TPU." And in case you're new to floating point arithmetic, you could check out this very elaborate article on the Geeks for Geeks website entitled IE Standard 754 Floating Point Numbers. That said, other data types like the booleans exist, the complex number, that's complex 128, complex 128, complex 64, double, float 64, have int 16, int 32, int 64, which is already, the QINT, the int 8, and all this we've seen already. There's also the string data type, string, and then resource and variant data types. Then we also have this unsigned integers. That said, we've seen the different data types. Let's test out this one. So let's say we want to have a QINT 16 right here. We change this because it's an int. So now we have this QINT 16, and then we could also have a boolean. So let's have this bool right here, and then if we run this, you see we have an error. So let's convert this into a boolean by having either true or false. So let's say we want to have true, true, and then false. So let's run that, and it works fine. So that's it. We have this boolean tensor right here. We could also have a string tensor. So we could have this hello world, and then we have tf the string. Run that. See, that works fine. We could put this in this array, or rather in this list. We have hello thanks, and have that, close that, run it again. There we go. We have this type string. Let's take some steps back, go back a little, and then we'll have this. If we have this, we would maintain the float. Let's say we have float 32, for example. Let's put 0.5, run that. We have this float 32, and now we'll see how we could move from a float 32 to a float 64, from a float 64 to a float 16, and so on and so forth. So let's create a tensor. Now the operation we shall be using here is what we call the casting operation. Now with casting, we're able to move from one data type to another. So let's take this off, and then we'll create a new. So we have tensor, or let's say casted, or let's just say C. Let's casted tensor 1D equals tf.cast. So not this, tf.cast, and then we have the tensor 1D. So we have that tensor 1D, and then we specify the data type we want to cast it into. Now note that here it was float 32. Now I want to cast it into tf the float, say 16. We'll run that. Okay, let's print that. So we print our casted. That's it. Run it, and there we go. We see that we have the same tensor but of two different data types. It means this second tensor occupies less memories compared to this one. Now let's cast it and put this as an int. So let's run that. There we go. We see that the cast operator is able to convert this from a float to an int. So we leave from 0.5 to 0, which is logical because now we're dealing with ints, and -3, and that. So let's put unsigned int, run that. See that this time around we have 306553 and all of that, because we've converted this from a float to an unsigned int. Now let's take this off and run it again. See, okay, now we have 303. Now we see that this time around everything looks almost similar because there was no negative sign here. Now let's take this off. We have that, run it. See, it's the same now. But nonetheless, these two tensors are of two different data types. So far, we've learned how to create tensors in TensorFlow using tf.constant. Let's now look at other ways of initializing our tensors. And as we said earlier, if there is any place where you could find any information you want to master TensorFlow, it's in its documentation. So right here in the documentation, we'll have this. So we'll click on this TF right here, and then we shall browse to look at methods which we could use in initializing or creating our tensors. Right here, scrolling down, you'll notice the cast method which we've seen already. Now let's go down, and we have this convert to tensor method right here. So there we go. We have this tf that convert to tensor, converts the given value to a tensor. Now note that sometimes you may be working with say a Numpy array or even a list. As you could see in this example right here, we could convert that Python object of a different type into a tensor by using the tf that convert to tensor method. Getting back to our notebook, let's import numpy as np. And if you've never used Numpy before, you could come to our platform, Essential Python Programming Course, which is actually a free course, so you could just simply gain access to this course freely. And in the section on Python packages, you would have a full Numpy course. That's it. We get back to the notebook. We've run this already. So now let's come right here, and then we'll say we want to have our Numpy array x. So we have x equals numpy.array. So we have our Numpy array right here, 3, 5. We'll print this out, x Numpy array, see here clearly. And then we could convert this. So let's have x tensor. So let's say this is xnp, this is xmp right here, and here is xtf. So xtf equals tf.convert to tensor of xnp. That's it. Print out xtf, yeah, and then you run it. So there we go. We'll run this. xnp is not defined. Oh, let's run this cell, run that again, and there we go. Now we see clearly the difference between xnp and xtf. This xtf is a tensor, while xnp is a Numpy array, and the type given here is int 64. We have the shape and we have the content of our tensor. Now this this convert to tensor method takes other attributes, so we could specify the d type directly in here. So let's say we have the float 16, run that, and we should get our new tensor. Here we have an error. Let's add tf to this. So we have tf the float 16, run that again, and we have this tensor of d type float 16. Our next method will be the tf.I method. This method constructs an identity matrix or a batch of matrices. So here is how we create this identity matrix using tf.I. So we have that copied out, and we head on to this right here. So let's have our identity matrix. So we have our identity matrix right here, equals tf.I. We specify the number of rows. Let's say we want to have 5 rows. Now for now, let's do it simple. So we have this taken off, and then we print out our identity matrix. So we have our identity matrix right here. We run that, and there we go. We have our identity matrix which has been created. And in case you have no prior knowledge on linear algebra, you should just note that this is a matrix, or the identity matrix is a matrix in which you have all ones on this leading diagonal right here. So notice how all these elements are ones, and then the rest are zeros. So when you specify that you want a 5, it means you want to have a 5 by 5 matrix, as you could see right here, and then we want these to be ones and the rest to be zeros. So let's change this to say 2, and you have this 2 by 2 identity matrix. Now we could include the number of columns. So let's suppose that we don't want a square matrix. A square matrix is one in which the number of rows equals the number of columns. Now in the case where we don't want to have this same number of row and same number of columns, we could modify number of columns right here. Could have say 3, and then we'll run that again. You see that we should have we have an error right here. Let's take this, run that. You would see that we have this matrix of shape 2 by 3, 2 rows and 3 columns, but this row still maintains. You see that starting from this position going in this diagonal, we have all ones. Let's take this to say 8, and you have that. You see we have all ones. And in fact, the actual rule used here is that every time the row number equal the column number, we set the value to be equal 1. So every time we have this condition right here, every time we have this condition, we set the value to be 1. In this case, for example, we have the 0th row, 0 column, so the value is 1. Here, first row, first column, value is 1. Here, second row, second column, the value is 1. And the rest of the values are zeros. Let's take this off. And then we could now specify the batch shape. Let's say we want to have 3 batches. Run that. We find that we have this error. Now, whenever you have this type of error, always make sure you go back to the documentation and make sure you understand exactly how this method is being used. That said, getting back to the documentation, at the level of the batch shape, we have a list or tuple of Python integers or 1D in 32 tensor. If provided the return tensor will have leading batch dimensions of this shape. Now we see clearly that we are not meant to put in a number but a list, so we used this poorly. And so right here we modify this batch shape and let's say 1 3. That's it. We run it now and that's fine. We see clearly that we've created 3 batches of our identity metrics. See clearly we have this one, this, and this. Now we could modify this to shape say 2, and then right here we want to have 4. We'll run it again, and there we go. We have 2 batches where we have each batch, which is 4×3 identity metrics. Could take this off, run it again, and there we go. The next method we'll be looking at is the fill method. So right here we have this fill method. What does it entail? Creating a tensor filled with a scalar value. Now you want to create a tensor of a particular shape filled with a particular value. So here we created 2×3 tensor, and then we want to make sure each and every element of that tensor takes the value 9. So that's it. See, it's not in any way complicated. You just need to follow this documentation. We get back to our code. We want to fill, so filled tensor, there we go, tf.fill, and then we specify the shape. So we want to have say 4×3, and then we specify the value, say 9. So that's it. We print out our filled tensor and we have our expected results right here. So we expect it to have this shape 4×3 and all filled out with a value 9. Let's take that to 19 and we have the value 19. Our next method will be the tf.once method. Basically in a tf.once method, all the values take the number 1 or are set to 1. So it's some sort of tf.fill, but this time around the set value is always equal 1. So right here all you need to do is specify the shape. Yeah, you could specify the data type and then a name. So getting back here, we have once tensor equals tf.once, and we specify the shape for 4×3. We run that. Let's print this out. Print out once tensor. While we run that, we could change this to a 1, and then we'll notice how we have exactly the same answer right here. See that we have this 4×3, 4×3, and this is all ones, this is all ones. There is a difference in the data type, which we could modify here. tf dot say float 16, and then right here, let's run this, and then right here, oh, we get in this error, and that is because this method doesn't take in a data type, so we can't specify the data type. If you want to change this into a float, all you need to do is to add this decimal right here. So let's rerun that again, and we see that we have now a float 32, whereas with this we could specify its d type. So we could say float 16, and this will work. So let's take that back to float 32, and we see how we create the same tensor using both the fill method and the once method. Another method similar to the once method is the zeros method. So all we could do is just simply replicate this right here. We have it, we just have this zeros, and then your zeros, and we change this to zeros. Run that. There we go. We see that we have the same kind of response or similar response with the ones, where all the values here are all zeros. We could also check out this once like method right here. With the once like method, what we have as input defines the output shape, but with the difference that we are gonna have the output with all ones, hence the term once like. Just like saying we are putting setting all the elements to values ones, but the shape is gonna be like that of the input. So let's copy this, and then right here paste it out. We have say once like tensor equals this, and then our input, let's define an input right here. So we're gonna have, let's just copy this, or let's just take an input we created already. So we wanna have an input like this one, tensor for D. So we wanna create ones like tensor for D. Okay, so we have here ones like tensor for D, no, for D. Okay, so we have that. We wouldn't specify any D type, no name, and that's it. Take that off. Okay, so we have this ones like tensor defined. We have here ones like tensor. We run that, and we have this not defined. Let's define this tensor. It's actually 4D, so let's copy that. We have it here, tensor 4D. Okay, so there we go. We see that we created this. Let's print this side by side. Let's have the shape, and then print out our tensor 4D shape. Okay, so we would have the shapes side by side. We see that we have exactly the same shape, and now when we print out tensor ones like tensor, we notice how we have all values taken up once. So this method permits us to convert or to create a tensor with the same shape as the input, but with the difference that all the values are ones. Our next method is a random normal initializer. So we just copy this out. There we go. We have random, let's say normal tensor equals this. Right here we are not having any specific input. We just have this mean, we have the standard deviation, and then the seed. Now let's start by the mean and the standard deviation. From here we move on to the range method, and this range method will be creating a sequence of numbers while specifying the boundaries. So we'll specify the starting point and the ending point, or what they call here the limit. Now you could as well specify the start and limit as you could specify just the limit. When you specify just the limit, we suppose that the starting point is 0. So right here you see this example, start 3, limit 18, delta 3, and then we have the output at tensor. So let's just have this. So right here we have our range tensor, which is equals tf the range. We specify the starting point, so our starting point is equals, let's say 2. Our limit is equals, let's say 10, and then we can print this out. So we print out our range tensor, and that's it. We have the values from 2 right up to 10. Notice how we actually start with 2, but at the last value we go up to limit -1. So we're going from start, the rule of thumb is from start to limit -1. So that's how we look at this. Now we've gotten this, we could modify the steps we take. Like if you notice, we're going one step, 1, 1, 1, and down to the end. So we're going 2 plus 1, 3, 3 plus 1, 4, right up to the end. And if we want to modify this, we simply modify delta. Delta equals, let's say 3. We run that, and now we have something different. 2 plus 3 5, 5 plus 3 8, 8 plus 3 11. So parses a limit, so we end here. That's it. Our next method is the rank method, which is the same as the say here. It's also known as the number of dimensions. We've seen this already, so we wouldn't get into redoing this in the notebook. You just have to note that in the case where we have this, for example, a tensor of shape 2 by 3, then the rank is equals 3, since the number of dimensions equals 3. We have another important method like the shape method right here. We could go ahead and directly print this out. So we have tf.shape of, let's say, range tensor. So let's run that. We have tf.shape of range tensor. We see that we have a tensor which contains the shape of our input tensor, range tensor. Now let's modify this range tensor and take a different tensor. Let's take this tensor 4D. So let's say, let's take tensor 3D. Tensor 3D. Okay, so we want to print out this shape. So tf the shape of this tensor 3D. We run that. We have this tensor which has values the shape of our input tensor. Notice that this is quite different from doing a tensor 3D dot shape. It's quite different. You'll notice this difference. You see here that we have this triplet 4 by 2 by 3, whereas here we have a list where each element or each item of our list happens to be the magnitude of each and every dimension we have here. Our next method is a tf.size, which specifies the number of elements we have in the tensor. So you could go ahead and check on tf.size. We could print this out. tf.size of tensor 2D. So let's run that. And there we go. We see we have 12 elements. Now let's modify this. Let's take 4D. And we have 72 elements. Now let's print out, let's look at what we had written right here. This 4D, since here we have 2 by 6, that's 6. 1 2 3 4 5 6 7 8 9 10 11 12. 12 times 6, 72, and that is logical because we have 72 elements given to us right here, or the output of this tf.size equals 72. Our next tensor initialization method is with the TensorFlow Random module, which we have right here. So we click on this tf.random, we have this overview, and then we checked out on this generator right here. So we have tf.random.generator, and then we have the syntax. If we scroll down, we could check on this example where we see exactly how this TensorFlow Random generator works. So right here we initialize this, or we create this variable g, which is equals tf.random the generator from seed. Seed is specified, and then we have g.normal and the shape is specified, and then we have this output of shape 2 by 3. So we have 1 row, 2 rows, and we have 3 columns, 1 2 3. But before, or instead of starting with this example, we'll instead take this example and later on explain what this actually means. So right here, let's take this example. There we go. We run that. We have this output. So we have, as expected, this 2 by 3 shaped output tensor. Now let's run it again. Now let's just copy this, or let's do a g. Let's simply have this. Let's copy just this. So we have g.normal, and we'll run that again. What do you notice? You'll notice that we have 2 different outputs this time around. So here we have an output, and then running this gives us another output. In case we even run this again, we'll still have another output. Hence the term random, as this model permits us generate these types of random numbers, or random tensors, or tensors which contain random numbers. From here we have this generator, and then specifying from non-deterministic state actually means we do not want to alter the way our random numbers are generated. So let's consider we have two experiments, E1 and E2. E1 takes in certain inputs which also contain some random tensors and then generates an output or generates some outputs. And then we have this E2 which takes in inputs and then generates to those outputs. If we have some random tensors in here, then the output we get from this will certainly be different from the output we will get from this. And this is because when carrying out this experiment E1, we had a different set of non-deterministic random numbers which are being generated. So in the case where we want to have these two experiments coming out with the same output, then what we could do is we make use of a seed. So using a seed, we are able to generate exactly the same random numbers which are going to be inputted in this experiment as with this other experiment. So by doing this, we're ensuring that the random numbers used in this E1 is the same random numbers used in the experiment E2, and hence we could get exactly same kind of outputs. So that said, we could modify this. Let's copy this and put it out here. We have that, and then we say from seed, and then we specify the seed. So this time around it's deterministic. So we have from seed, and then we'll say, for example, 120. Run that, and we should have this. So let's copy this. So we have g.normal. Let's run this again, and you'll notice something. You'll notice that we have this response. Now let's rerun this again. So we see that you'll notice that we have exactly the same random numbers generated each and every time. Let's take this to say 2 and this 2. So here we run this. See 0.3, 1.18. Run that again. You see a different set of random numbers. But with this, when we run it, we have the same or exactly the same random numbers each and every time. Negative 1.76, 1.48. You see, always the same, whereas this always changes. So in cases where you are dealing with random numbers, or you want to work with random tensors, and you want to ensure that that experiment is easily replicable, then you would have to use this from seed right here. Now we haven't yet talked about this g.normal and all of that. Now obviously you understand that specifying the shape specifies basically the kind of tensor you want to produce, or the shape of the output tensor. But then what is this normal we always have in here, and what if we modify this? Like we could have a uniform right here, uniform. Run that. We have this tensor generated. Run that again. See, we have that. We could change this to uniform. So we could have uniform. Run that. And we have this random tensor generated. Coming back to the documentation, you'll see the different methods right here. So you'll notice the from seed, which we've seen already. You'll notice the normal, and you'll notice the uniform. You could also use a binomial in place of the normal and the uniform. And you could check out the rest in the documentation if you want to better understand it. You always have, for example, like in the split, returns a list of independent generated objects. So basically you have the explanation to each and every method you have here. Let's go to the normal. You'll see here we have normal, specify the shape, and we have this two arguments right here which we haven't spoken about. We have the mean and the standard deviation. Now the d type is what we've been seeing, and the name too. So we have the mean and the standard deviation. Now what is this all about? To better understand the normal method, we could check out this probability playground from the University of Buffalo by Adam Cunningham. As you could see here, we have a normal distribution which takes in parameters mu and sigma square. Now this mu is the mean, so what you call the expected value is actually the mean, and the sigma is the standard deviation. Sigma square is the variance. Then this normal distribution happens to have a probability density function. So if you have no background in probabilities and statistics, do not bother too much about this. You could just get straight to this curve, or this bell-shaped curve right here, where we'll be playing around with the mean and the standard deviation, or with the variance. So right here we have the mean and we have the standard deviation square, or we have the variance. We modify this mean, so let's take the mean to a value of, like, as you can see here, a value of like 10.51, and then the standard deviation, let's reduce it. You see, reducing the standard deviation makes this curve appear thinner, while increasing the standard deviation, as you can see, makes it appear wider. So what does this mean? We're supposing that, for example, we have a class of students where the average mark is 10.51. So if we're supposing the mean to be 10.51, then we'll be around this point right here. And if we say, for example, that the standard deviation is 5, then let's take this off. Then we'll be having sigma squared to be equal to 25. So let's go down to 25. 25 will be around this. Okay, so we have that. So if we go down to 25, we'll be around that. Then this curve simply tells us how likely we are, or a student is, to have a certain mark. As we could see clearly here, we have this peak at 10. So if we have an average or expected or mean value of 10, then it means we are most likely to have a student, or if we pick a student at random, that student is most likely to get a score of 10. That's why we have this peak at the mean. Now, the standard deviation tells us how much the student's marks could swing away from this mean position. And that's why whenever we reduce this, so in the case where we had reduced this to, let's say, 1, when the standard deviation is 1, we have sigma square, which is also equal to 1. We have values just around 10. So you could look at this, you'll notice that we have values just around 10, and getting a value like 4 on 20 practically has a probability of 0. Getting a value of 20 on 20 has a probability of 0. So it's very improbable for us to pick a student and the student has a mark of 20 on 20, because we've initially said that the standard deviation is 1 and the mean is 10, in this case 10.51. So we have that. Now increasing the standard deviation to some higher value, like say 31, or let's take some reasonable value, let's say 25, let's say 25 here, let's take 25, or this 12. Okay, so increasing the standard deviation to this simply tells us that we're now able to have more students who can, or picking a student at random will increase the chances of a student who has been picked at random to have a mark of 20 on 20. As you can see right here, 20 on 20, we see that we have a higher probability of getting a mark of 20 on 20. And this is because we've increased our standard deviation. So let's move our mean. So let's take our mean value. So if we suppose that students, most of the students are having marks of, say, average marks of 14, that would be a very good class. You'll see that our standard deviation now, even if reduced, will still lead to students, or will still have a high probability of students having marks of 20. So that's it. We could check on other distributions right here. We have this uniform distribution. Now this is the other distribution which is available in TensorFlow. So right here we have that, or we have these two parameters a and b. A is the lower bound of the interval and B is the upper bound of the interval. We're going from this lower bound to this upper bound. So if we change A, let's say A, you see, let's modify A to a value of say -2, and then B to a value of say 2. We see how we modify our rectangular shaped uniform distribution right here. Now with a uniform distribution, as the name goes, uniform, just any value between -2 and 2 has the same probability of occurring. So unlike with the normal distribution, where it's normal distribution, unlike with the normal distribution where those values surrounding the mean have a higher or have the highest probabilities of occurring, with the uniform distribution, every value which falls in the range has the same probability of occurrence. Now let's get back and see how this translates to our TensorFlow code. We modified this uniform. We start with a normal distribution, normal, and then we specify the mean. We have a mean of say 0 and standard deviation of 1. So let's start with this. We run that and we get this error. We should modify this to std_def. So that's it. Run it again and there we go. We see that we have this value 0.97, 0.89. Let's run that again. 1.70, 0.05. Now let's modify the mean to a value of say 100. If we modify this mean, you'll now notice that there is a change in the way these random numbers are being generated, as these numbers now are generated around those mean values and take into consideration the standard deviation. If you notice, we run this, so we see values are just around 100. If we modify the standard deviation to say 100, you'll now notice that we have values around 100 but which deviate more from 100. You see 177, which wasn't possible when we had a standard deviation of just 1. You will never get 177 with a standard deviation of just 1. So that's it. Now let's take this. We see how we're able to control the way these random numbers are generated with the parameters mean and standard deviation. Now let's look at the uniform distribution. So with this uniform method, let's run this again, and now let's specify the parameters for the uniform distribution. We click on this. We have the mean value and the max value. So by default the mean value is 0, and we get back to the code and specify the mean value equals say 23. Or let's say we have this mean value equals 0, and then we have the max value equals 100. So we'll run that. We'll modify this mean val, your mean val, run that again, and we see that we have these values 6.97, 86.12. Now that sounds great. Let's increase this maximum value. See, we have these values. You see that actually by increasing the values, we are simply saying we want to get a random number in this range. So if we want to get a random number in this range, we simply put this out like this. Now let's take this to 10. See that we have that. See, values now will only fall in this range 0, 10. Let's modify it. Oh, we even picked the seed. So let's take this off. Let's have from non-deterministic state. So let's take this off from non-deterministic states. That's fine. Run that, and there we go. So we see that we always have these values between 0 and 10. Now let's take this. Let's take a value, say 12. You should have an error. Now let's take this, say 12, and then your say, oh, let's take between 25 and 40. Run that. We see we will always get values in this range. So that's how we're able to specify the range. Another distribution you could check on is this binomial distribution right here. So that said, you could check on these other methods. If we get back to TF the random right here, tf.random. We also have this, that's tf.random.normal. So you could directly use the normal distributions like this. We have tf.random.normal, and here you specify this directly, and you could also specify the seed. So in the case where you don't put in the seed, it means you do not want to use a seed. We paste this out in here. We have our random number. Let's just print this out, or let's just leave it. So we have that, and then we specify the shape. So here we have 3 by 4, the mean, the standard deviation, the type, the seed, and the name. So we will not do this now, or let's just put this name. Let's say random number with random number. So let's do that. Random number with normal distribution. So we run that. There we go. We have our random number, and then let's reduce this so we'll see that clearly. There we go. We have our normal distribution. You notice that the values are all revolving around the mean, and they span in a way that they reflect the standard deviation. So in case I put in 0 0, that's 0 0. Oh, an error. Let's say we have here 0 0. You will notice that you have much larger kinds of random numbers generated. Similarly, we could do the same for the uniform distribution. We'll specify the shape. So we have here 3, let's just take 2, and the minimum value with a maximum value. So we have that, and run it. Here's what we get if we modify this to 100. See the kind of values we get in now. Now we're gonna move on to tensor indexing. So let's take this example. We have this tensor to be indexed, and we declare this. We have this tf constant and this 1D tensor. We print this out. This is what we get. Now, supposing we want to get this first 4 elements. To get this 4 elements, we need to consider this the indexes. So here we have the 0th index. Then here we have the first index. Here the second. Here the third, and the 4th. So we want the first 4 elements. All we need to do is take out this first 4 elements by doing this. So we have indexed, and then we have the square brackets. We start with a minimum index, that's 0. That's the 0th index, which is this. We go 1 2 3 4. Now here we specify 4. There we go, and that's what we get. We have this first 4 elements right here. Now you might have noticed that the 4th index is actually this here, but then since we're starting from 0, our 3rd index happens to be the 4th value. So if we're taking this from 0, we have 1 2 3 4. So here are our first 4 values. Now note that if you want to go from the 0th or from the first, let's say we want to go from this index here 6 to 66. If you want to go from 6 to 66, what you will have to do is this. We have that. We pick out 0. We go start from the first 0 1. So we have this 1 right here, the minimum, and then we want to go up to 66. Then we'll have to go 1 2 3 4 5. Now if you put this 5 right here, you'll notice that it's not gonna give you exactly what you want. So let's run this, and then we get that. So you see that we have here 6 2 4 6. We actually have this instead of all this. So how do we do to get all this? In order to go from one index to say a maximum index, what you need to do is to add this plus 1. So if you want to go from the first index to the 5th index right here, that's 1 2 3 4 5. I want to go up to this index. I need to put this plus 1. It's similar to with a tf.range we had seen previously, where in order to put out a tensor from, let's say, a range 2 to 5, what we needed to do was to specify this from 2 to 6, so that it would be like 2 3 4 5. So yeah, what we did was we had 2 5 plus 1. So it's a similar kind of pattern that we're following right here. So to go from this up to 66, we need to add +1. So let's run this now, run that, and there we go. We have exactly what we expected. So let's take this off now, and we have 6. So with this, we see how we're able to slice out some parts of this array of this tensor. From here, we could also include steps. So if we put out, say, 2 steps of 2, you will notice that we go from the first, that's the first index. This is the 0th index, so we'll go 0. We start with this 1. We skip by 2, so we skip this element, and then we go straight to 4. So notice how we go to 4, and then from this 4 we skip this element, and then we go to 66. So that's it. So we could include the steps right here. Now by default we have a step of 1. So when we do this, you see we have exactly what we get when we don't put the steps at all. So that's it. We've seen that in general we have a minimum value right here, and then we have a max value, or rather a max index. So yeah, we have, so that's it. In general we have a min index up to the max index +1. So generally this is what we get. Now in the case where we don't specify this min index, that's if we have this, for example, let's suppose we have this, we don't specify any min index, and then we go up to 4, then this is considered to be 0. So you'll notice that these two come up with the same answer. We have exactly the same answer right here. When you specify the minimum value, say 3, and you don't specify the maximum, we just gonna go right up to the end. So let's run this. We'll see that we'll get 0, 1, 2, 3. So we're gonna start from this and then go right up to the end. So we'll have 4, 6, 66, 7. So that's it. We have exactly as expected, 4, 6, 66, 7, because we start from 3, and we're going right up to the end. If we want to go from this first, or from this minimum index right up to the last but 1 value, that is, want to go from this 4 right up to 66, what we could do is have our maximum value to be -1. So doing this, you'll see that we have 4, 6, 66. So we're going from this index, this minimum index, to the last but 1 value. Now let's take this to 2. You see we have 4, 6. Take this to 3. We just have 4. Take this to 4. This should be an error. From this point, we'll see how indexing is done with tensors of dimension greater than 2. So we'll start with a 2-dimensional tensor, which we had declared previously. Now for indexing to be done, we'll start with a comma right here. So we have this comma, and then if we want to get the first 3 rows, so suppose we want to get this first 3 rows, and then in this first 3 rows want to get just the first 2 columns. So we want to get this column and this column. In fact, what we want to get is this 1, 2, 3, 5, 1, 5. This happens to be the first 3 rows and the first 2 columns. So in order to do this, we note, as we said here, we have this comma, and then to this left side we have the rows, and then to the right side we have the columns. So what we do here is, since we want to get the first 3 rows, we're going to go 0, 1, 2. So what we're going to have here is 0 right up to 3. So we're going to get 0, 1, 2. Obviously 2 plus 1, 3. So we have this. So it's kind of like similar to what we've seen already here, but with the difference that all this, let's say all this, gets to this left side. And then for the columns, or rather for this, for the columns, we want to get the first 2 columns. So what we're gonna have here is 0, 2. So we'll have that. There we go. And then let's run it. So running that, we say we have 1, 2, 3, 5, 1, 5. Now let's suppose we want to get this first 3 rows like this, and then want to get all the columns. So basically, what we can do is this. So just like you're getting all the elements, we just had to do this. That is with this column. Here we just have to put this column right here, and then we're good to go. So let's run that, and we should have 1, 2, 0, 3, 5, -1, 1, 5, 6. So we've gotten the first 3 rows and then all the columns. Now if we want to get a particular row, so suppose we want to get just the 3rd row, That's want to get only this row right here. We're gonna specify its index. This is 0, 1, 2. So here we have 2. So for the rows, recall we have the left side representing the rows and the right side representing the columns. So yeah, what we're saying is we're getting the second index, or this row, the second index, or this third row, which happens to be this. And then for the columns, we're getting each and every column. So let's run this. We should have 1, 5, 6. Now, if we want to specify, or if we want to get just some of these columns, that's if we want to get maybe only this column right here, we're gonna have 2, and then we'll specify the 0th column. So we'll run that, and we should have 1. Now, if we want to go ahead and take, say, 1 right up to the end, you see we'll have 5, 6, because here we'll specify we want to get the second row, that's 0, 1, 2, second row, and then for the columns we're going from 1, this 1, because this is 0, 1, 2, 1 right up to the end. So that's it. Just like with the rows, we could also specify, or we could also get just a particular column. So suppose we want to get this 0th column right here, which is made of 1, 3, 1, 2. So to have that done, we're taking all the rows. So we're gonna have all the rows, and then we will pick out just the 0th column. So let's run this, and we have 1, 3, 1, 2, which is this column right here. Now let's take this from here, and we see we have an error because we haven't specified how these rows are going to be managed. So here again, let's say we want to take 1, 2, 3. So right here we have 3, 1, 3, 1, because we're picking for the columns, we're taking the 0th column, so we're taking all this, and then for the rows we're going for 1, 2, 3. So 0, 1, this is our first, this 1, 2, and then 3, meaning that we're stopping at 2 because we're stopping at 3 minus 1. So we're taking this and then this, and then since we're taking the 0th column, we just have 3 and 1. So that's how we get this. So let's come back. We have this, and then if we want to pick out the column on the first index, we have 2, 5, 5, 3. Now this here means we're picking up all the indices. So if we're picking up all the indices, what we could do is specify just this 3 dots. 3 dots simply means picking up everything. So we're picking up all the indices, or we're picking up all the rows, and then we're specifying the first column. So running this should give exactly the same output as we could see right here. We now move to the 3D tensor. So we have this 3D tensor right here. Let's take this off. Now we kind of like very similar to what we've seen already with the 2D tensors, but with the difference that we have the 2 commas. Now we'll explain why we have these 2 commas. Recall that with 3 dimensions, we have the first dimension, the second dimension, and the third dimension. So first thing, let's put this way. Let's have this. We have this. Each of this is a 2 by 3 shaped tensor. So here we have 2 by 3. We're just putting out the shape actually. And then here we have 1, 2, 3, 4 elements. So we have 4 elements. So this happens to be the shape of our 3D tensor right here. Now if I want to pick out just this first element right here, all I need to do is to specify a 0, and then I could take all this. All this simply means that I've picked out this first index and then taken all the rows and all the columns. So let's run this, and you should get just this right here. So we see we have 1, 2, 0, 3, 5, -1. So that's fine. Now if in this index, that if after selecting this index I want to say get only this first row, what I'll do is I'm gonna take 0, and then right here I'm gonna pick everything. So I'll run it, and I'll have 1, 2, 0. I have only this right here. Now if I want to get this last column, what I'm gonna do is I'm gonna specify I want to get all the rows, and then for the column I want to get the last column. So there we go. I have the last column, 0, -1, because I'm starting from the end actually here. Now another way we could do this is by saying, okay, I have 0, 1, 2. So I'll take the second index, run that, and I should have the same answer. So that's it. Now if I want to go from 0 to 2, so I'm going to pick 0 to 2 means I'm picking 0 and 1. So I'm picking this 2 actually. Picking this 2, run that. You see I have 0, 0, negative 1, 2. Or rather I have 0, negative 1, 0, 2. The reason why I have this is because right here I have the 0, negative 1, and then here I have 0, 2. So that's it. The 0, negative 1 is because I've picked these two indices. So 0, negative 1 is the last right here, the last index or the last column. Pick out the last column, and then for this I also pick out its own last column. So that's how this works. We just have this commas which separates this. Now another way I could do this is I could take all. So doing all, I should have exactly the same response. So instead of having that, I could just put out this 3 dots right here. Then here I could pick out all. So here I'm supposing I'm taking all this. Since we're picking up all this indices, that's we're picking up 1, 2, 3, 4, all these 4 elements. We're picking up for each of these elements all the rows, picking this all the rows, and then for each of these we also pick up just the second column. So if we're picking up all those rows and just the second columns, then we'll be left with 0 for this and negative 1. Then for this we're left with 0, 2, there's 0, 0, there's 9, 32. We now move on to TensorFlow.math, which you could see clearly here. We'll be able to use all these math functions which are made available with TensorFlow. So as you could see, we go right up to this zeta functions. We're starting from the apps function. This apps here, clicking on it, we would have tf.math.apps. And note that for each and every function, you'll have the function definition and you will have an explanation. So like you have this kind of example where the function has been applied, and you'll be able to understand exactly how those functions are used. So in case you want to understand how the A102 function works, just click on that. You have this. We clicked on a sign actually. Let's just work with a sign. In case you want to work with the a sign, you would have this. You have this example, and then you get this explanation on all these arguments which get into this function, like the x, you have the name, and then what it actually returns. So you don't need to always figure out by yourself how these functions work. You just basically need to make good use of this documentation. Now that said, let's look at a couple of functions. We have the abs function. It's actually the absolute value, so it gives the absolute value of a tensor. Now to get the absolute value, we simply pass in the tensor. So like in this case where we define this x, so x abs, we have the x, which is this tensor right here, and then we could get the absolute value very easily. So we have that, we run it, and you see we have the absolute value. Now what's an absolute value? Absolute values are defined as such: if the number or the input is a negative, so if the input is a negative, it sends it to positive, so it turns it into positive. If the input is a positive, it turns it into a positive. So it remains the same, or basically here it remains the same. So that said, we could say, for example, tf.apps of, say, tf.constant 0.2. If you run that, you'll see you still have the same. Now, if we turn this to negative 0.2, you would have still 0.2. So it takes it from a negative number to a positive number. Or basically, we can say that the absolute value of x is negative x when x is less than 0, and is equals x when x is greater than 0. So if we have a positive number, it remains the same. And if we have a negative number, you attach a negative sign, and obviously a negative with a negative would turn this to a positive. So that's why when you have this negative 0.2 here, you have negative of negative 0.2, it turns into 0.2. So that's it for the absolute value function. You could also check out when we have the complex number. That is, if we have a complex tensor, you could check out this absolute value function right here. The inputs of this absolute value function can also be complex numbers. Now, if we have a complex number, say a plus bj, then its absolute value is computed as a squared plus b squared, all of that, square root. So if we have negative 2.25 plus 4.75j, as you see, it looks exactly the same as a plus bj right here, then we would have the absolute value, or get the absolute value by doing negative 2.25 square plus, or rather the square root of negative 2.25 square plus 4.75 square. That said, let's take this off. Let's just have one. So if we have just this one right here, okay, now we run this x-apps complex, and then here we have x-apps complex 2 complex. Okay, so let's run this and you get this output 5.25. Now let's do a squared. Let's take this. If we have the square root, we'll be using the square root method. So we have tf the square root of negative 2.25 square. Notice how this pops up right here with the definition, as with the documentation of the square root method. So we have the square root, takes in this input, and then name. So basically we're just finding the square root of all the elements we have in our tensor. So that's it. We have negative 2.25 plus 4.75 square. So 4.75 square. So that's it. We compute the square root and we see that we do not have the same answer. That's because we didn't put this in the bracket. So there we go. We run this again and we see we have exactly the same answer. So we now check on the addition. So here we look at this addition function. This can be seen as element-wise addition. So supposing we have x1 and then x2, tf dot constant, we have say 7, 6 to 6, 7 and 11. D type, let's specify the D type, tf dot int 32. We could simply do tf dot add x1 and x2. So let's run this. We get our output. It's basically the addition of all these elements. So it's an element-wise addition. Now you could check out other methods like multiply. So you could have multiply. We run that. See 5 times 7, 35, and so on and so forth. You could check out subtract. So you could have here subtract, and you have your answers. Let's check out divide. There we go. Run that. There we go. 5 divided by 7, 3 divided by 6, and so on and so forth. Then we also have other interesting methods like this divide no nan. So in the case where you divide into values and you expect it to have a nan, like when you divide them by 0, you expect it to have a nan that's not a number. This method takes care of that exception for you. So let's come in here and instead of 0, run that again. You see we have this. Now let's this infinity. So let's now say no nan, run that. We have this error because this is actually math, so you should have that. We have here that tensors of type int32 are not allowed. So let's take, for example, a float. So let's change this. We have float. There we go. Run that again and it's fine. So you see that when you have this, like if you are having a problem where you just want to have this nans or this outputs where it's meant to have infinity give you a 0, then you could use this method right here. Now note that it's not every time that when we're doing this element-wise operations that we have the two tensors being of the same shape. So that said, we could modify this. So let's take this to be just 7 right here. Let's take back the add. So we have add and run this again. You'll notice that we were able to do this addition, but with a difference from the others where the two tensors had the same shape, in that here we have the 7 which adds up to each and every value we have right here. So 7 plus 5, 12, 7 plus 3, 10, and so on and so forth. Now this is what we call broadcasting. In broadcasting, we have this smaller tensor which is stretched out to match the shape of this bigger tensor so that the operation could be carried out. So in fact, what's going on here is you have this x2 right here which has been stretched out. So we could see x2 stretched, and then what we actually have is this. So finally, when we carry out the operation, we have this 7. Let's make sure we have this values right, 7, and then we have this last 7. So basically this is what we have. Now let's print this out. Let's copy this, and then we have x2 stretched. That's it. Now we run it and we see that we have exactly the same output. So in fact, when you put this TensorFlow does broadcasting, and this tensor right here is been stretched out like this, and then the operation is carried out. So we could test this out with multiplication. Let's modify this. Supposing we have this right here, we have that, say 5, 45, so on and so forth. Okay, so we have x2 and then we have x1. Now let's still run with the addition. Let's take off the shape, run that, see, give the same answer. We go to multiplication, multiply, there we go. We run it again. We see we have this element wise multiplication. Now another slightly more complicated way of looking at this is when we have a shape, or when we have a tensor where one of the indices has a length of 1. So if we take this off, let's take this other one off. So if we take this one off right here, you see we have a shape of 1/6. Now let's define x2 differently. Let's take off the x2 stretched from here. So let's define x2 differently. We have, in this case, instead, let's define a 3/1 tensor. So we would have this, we have 5, we have 3. So there we go. We'll run that. Let's take this one off. Let's print out the shapes actually. Let's print out x1 dot shape, print out x2 dot shape. There we go. We have, this is x1 1/6, x2 3/1, and then the output of the element wise multiplication is this matrix we have here. So now let's explain how we get this matrix. Yeah, if we write this tensor right here, we would have this. It has just one row, so we have one row and then 6 columns, as you can see here, and then this other where we have 3 rows and 1 column. Just this 1 column, 3 rows, 1, 2, 3. Now that said, when we want to carry out the operation here, we take into consideration the fact that we have 3 rows right here. So what goes on is this one row is stretched out. So it's stretched out such that we now have 3 rows to match up with these 3 rows we have in this x2. So that said, we have now 5, 3, and finally 6 right here. So there we go. We now have this new tensor. That's it. And then for this, you should guess it right. We're gonna stretch this out such that the number of columns match with the number of columns of this. So basically, we're just gonna rewrite this 6 times. There we go. 3 right here. We're reading this 6 times. We'll stretch this out, and now we could carry out our multiplication operation. So let's take, for example, this element. We have the 6 times 5 right here. We should have 30. So that's why we have 30 here. And if we take 4 times 5, 20. That's why you have 20 here. If you take this 4/3, that's why we have 12 right here. So we have that. As a rule of thumb, both should have one dimension of length 1, as you could see here, and then the other dimensions are stretched so as to match one another. Our next method will be the TF.maximum method. So there we go. We have TF.maximum, which gives us the max of two tensors, or better said, the element-wise maximum of two tensors. Now this should be the same with the minimum, which returns the element-wise mean of two tensors. So that said, if we have these two tensors x and y, you see that we're gonna have here -5. So -5, 0, -2, the mean is -2, -2, 0, 0 means 0, 0, 3 means 0. So that's it. As you could see here, this surpassed the broadcast semantics. That's the broadcasting we've just seen. So that's it for the maximum and minimum. We also have the arc max and the arc mean, which we're gonna see shortly. So let's go. We have the arc max. Okay, that's it. Now with the arc max is a slightly different syntax. Here we have an input and then we specify the axis. So let's copy this B right here. Let's copy this tensor, paste this out. There we go. Okay, we have this B, or we have this arc x arc max, for example. So we have this tensor. Let's rewrite this. We have this tensor here, and then let's print out x arc max dot shape. Print out the shape. Okay, now we want to get the arc max, but before looking at the arc max of this tensor, let's look at a simpler tensor. So let's take something simpler. Let's have this. Let's say we have, let's close this. Okay, so we have this, and let's print out x arc max. We have tf.mat.arc max of this, and then we have that. We have it. Okay, so let's run that. We see that we have a value of 2. Now, why do we have this value of 2? Why do we, like, with this matrix given to us, have this 2 here? Now, what if we modify some of these values? Say, let's take this to be 200. Let's take this to be 120. Let's take 130. 0.3. Run that again. Oh, we have this. Run that again. We see that now this value changes to 0. Why does it change to 0? Now, if you notice previously, like, let's copy this again. Let's paste this out here. Let's take now this, or let's take this to that. Okay, you'll notice that with this, the position of the maximum value is the 0th index. Now, if we have here, this is our 0th index, this is our first index, this is our second index, here our third, and then here our fourth. So where is the maximum value here? You guessed it right, is 200. Where does it fall? 0th index, and so the output is 0. Let's take this other example. Where does the maximum value fall? It falls here. Where's the index? 0, 1, 2, 3. And that's why we have this. So actually the arc max is different from a max in the sense that here we're actually looking for the index, or the position of the maximum value. So that's it. If we want to have the mean, we just have to change this to mean. So we could have mean. Run that. You'll see we should get this here. So we have 0, 1, 2, 3. That's it. This is the minimum value. This position is the third position. Now, if we change this to mean 2, we have that. We should have this last position, 0, 1, 2, 3, 4. So that's it. Now, when we're dealing with multi-dimensional tensors like this one right here, we can specify an axis. So let's do this. We print out tf.mat.arcmax of x max, or x arc max, and then we'll specify the 0th axis. Now we'll look at the output and we'll explain why we will have the output. So here we have 22022. Now let's understand why we have this output given to us. Notice that right here we had fixed the axis to 0, and so that said, we are actually fixing the rows. So we have a row, we have these 3 rows, or let's take this, we have this 1 row, we have this row, and then we have this row, and then we're doing comparisons on the each element or the corresponding elements on each row. So it turns out now to be the column. So here we compare this 2 that's on this row, we compare this 2 with this 3 with this 14, and then here we compare this, here we compare this, here we compare this. Let's take that off. Here we compare this 3, 1, 5. Here we compare 6, 8, 27. So that's it. So when you fix the axis to 0, it simply means comparison is done on the other axis. So in this case, that other axis is a column. So we're doing comparisons on each and every column. Now, what is the maximum value here? The maximum value is 14. Where does it fall in this in the tensor? If we have this tensor 2, 3, 14, we see clearly its position. If the axis, we have the 0th position, first position, second position. So we see that it falls on the second position. That's why here you have this 2. Now if we look at this, our maximum is this, falls in the second position. That's why you have 2. We continue to this. Our maximum here is 30, falls on the 0th position. If you want to look at it clearly, we have 30. Extract that, we have 30, 16, and 23. Our maximum falls here, the 0th index, 0, 1, 2. So that's why you have 0. And then for the next, you have 5. And then here we have 27. That's why we have this 2, 2, 0, 2, 2. Now let's take this off and then change this to mean. So change that to mean. So we have a different answer. We have here 0. Our minimum is this. Next is 1. Our minimum is this. Next, our minimum is this. 1. Minimum is this. 1. Next, we have this. Okay, so that's it. Now let's modify this axis. So we change the axis. Now we will be working on each row. So we'll be doing comparisons on this row, comparisons on this, and then comparisons on this. So if you've understood what we've seen previously, when the axis was equals 0, when we had axis equals 0, then you should be able to pause at this point and then try to solve that for when the axis equals 1. So that said, let's explain how this works. We're gonna have comparisons with this. So the maximum here is, or the minimum, since we've changed this to mean, our minimum here will be 2. Here our minimum is 1. Here our minimum is 5. So that said, we're gonna have 0, since our axis position is 0, or we're on the 0th index, and then here we are at the 0, 1, 2, 3, 3, and then here we are at 0, 1, 2, 3. So we're gonna have 0, 3, 3. So let's take that off and run it, and we have 0, 3, 3 as expected. We have other functions right here. We have the equal function, which could be used to compare tensors. So we could compare 2 tensors, and in the case where each and every element is the same, we're gonna have this output Boolean tensor. So you see D type bool, and then here we have true true. The reason why we have true true here is because this element 2 is the same as this, and here 4 is the same as 4. Now we see again broadcasting here where we have 2, 4 compared with 2, 2. Now if you have a 2, it's broadcasted to match the shape. So this 2 turns into 2, 2. Now the first 2 compares with this 2, it gives true, and the next 2 compares with false. It's not, with 4 is not the same, so it turns into false. So that's how we look at this. We have the documentation here. We could look at other methods. We have this power method right here. We have we have the power method. We basically, to get the power or to raise all these elements, we're given power. Let's copy this so we better understand that. Paste this out right here. Scroll down. Okay, so we have this X, we have the Y, and then let's understand this power. Now basically what you should understand here is, let's reduce this to say 0, and then here 1. Okay, so as we're saying, let's take this to 4, so we should have 81 there. So what we're having here is we're taking 2 to the power of 3, 2 to the power of 0, 3 to the power of 1, 3 to the power of 4. So if we run this, take this off. If we run this, you see clearly we have 2 to the power of 3 is 8, 2 to the power of 0 is 1, 3 to the power of 1, 3, 3 to the power of 4, 81. So that's how it works. Now we could have TF dot power, and then TF dot constant of say 2, and then TF dot constant of say 3. So we have that, run it. There we go, we have 8. Next will be this reduces. We have here the reduce all, reduce any, reduce Euclidean, reduce max, mean, prod, STD, sum, variance. Let's start with the reduce sum, which is kind of like the most popular of all this. So we have the reduce sum. What goes in here is it takes in the input tensor axis, keep dimension set to false by default, name none. So it computes the sum of elements across dimensions of a tensor. So again here we're specifying the axis and we're going to sum through all the elements in that axis. So let's look at some examples. We paste this out right here. So we have this input tensor. Let's copy, let's work with one of the tensors we had declared previously. So let's have this tensor 2D right here. We have tensor 2D. We have it here. Okay, tensor 2D. There we go. Now we want to print this out. Print of this. We have that, and then in here we have our tensor 2D. Tensor 2D. There we go. We specify the axis. Let's let it like that. Let's first run this and see what it gives us as output. So we told we have an error. We then close this, run that again. Okay, so we have this here. First of all, this is this 2D we created, we printed it out. Let's run this. Okay, so now we have this value of 35. How do we have this value of 35? When you don't specify the axis, what goes on here is we just add up all elements. So we reduce all elements, or we reduce the tensor, and then this reduction is done by summing all the elements which make up this tensor. 1 plus 2 plus 0 is 3, 3 is 6, 11, 10, 11, 16 plus 6, 22, 24, 27, and 35. So that's how we get all this, or rather that's how we get this, by summing up all this. So it's a reduced sum. That said, we could do a reduce max. So reduce max, there we go, we have 8. So what goes on here is we're reducing all these values into just its maximum value. So we see with the sum we're adding up everything. With a max, we're just looking at the maximum value. So if you change this to, let's say we take this to 100, you see you get now 100. Now if we look at reduce mean, you run that, you should have 0. So that's it. Let's take negative here, run it. Okay, we have -2. So that's it. Now let's go back to our reduce sum, and then let's specify the axis. Let's say the axis is 0. Let's print back the shape of this tensor 2D dot shape. Let's run that, so we get a shape. Okay, it's 4 by 3. Now we'll specify the axis 0. Now we have 7, 11, 40, or 114. Now why do we have this? Specifying this axis 0 means we're fixing the axis all the way, like taking a fixed position on this axis 0, and then we're playing around with the other axis, which is the axis 1, and which happens to be the column, because we have the rows axis 0, and then we have the columns axis 1. So what goes on here is we're now doing this. We comparing, or rather we're summing up. We're reducing this into 1. We reduce this, and then we reduce this. So 1 plus 3 plus 1, that's 5, plus 2, 7. So that's how we have this. -2 plus all of that, 11. If you add all of this, you have 114. So that's how we get this, by when we fix this axis to 0. Now let's fix the axis to 1. You'll see that we've fixed the columns and we're playing around with the rows. So here we compare this, or rather we sum this up. Summing this up, we have -1. This should be 108. This should be 12, and so on and so forth. So let's run it, and we see that we have -1, 108. 12, 13, and that's it. So that's how we look at this. Now we could go back to max, reduce max. That's it. We could go to reduce mean. You see 0, 36, 4, 14. Now the mean is like the average value. So let's take this axis. Oh, let's take the axis 0. Run it, and we have that. Now what's the mean of this? When we're comparing this, we have 1 plus 3, 4, plus 1, 5, plus 2, 7. 7 divided by 4 is 1.75, but since we're dealing with integers, we just have 1. So let's change this d type. Let's say we want to have a d type of tf the float 16. So we run that, and there we go, we have 1.75. So that's it. We just calculating the mean of each on each of these columns, because we've decided to fix the rows, and then we're playing around with each and every column. Now we could change this to standard deviation. Standard deviation, we have that 0.829, 2.86, 41.38. So that said, we now look at the keep dims. Now take a look at this shape right here. We just have this one dimension tensor here. Now when we do this when we send this to true, we run that, we see that this turns into a two-dimensional tensor with the same elements, but we've added this extra axis or this extra dimension right here, and you could actually get to see this explanation from this. So that's it. We've looked at the reduces. We reduce max, mean, std, prod, variance, and all of that. Now we continue our journey through our math functions. We have this sigmoid, which is one of the very popular method. The sigmoid, we're gonna see this is basically this formula. It's basically this function. So y equals it takes in x, and then what it does, it takes the exponential of negative x, 1 plus the exponential, and then 1 divided by 1 plus the exponential. So basically this is this function, and then when we run the sigmoid, we just take each and every element and then pass into this function. Our next method will be this top k math function. With the top k, what we're doing here is we're taking as input our tensor, and then we're taking the top say if k equals 2, we're taking the top 2 values, just like in a class of 100 students, and then you want to get the top 10 students. Is kind of like the same function. So that's it. We have that. Let's see how that works in the notebook. So here we have top k, right at tf the math dot top k, and let's just take in this tensor 2d right here. So we have this tensor 2d, we run that, we get this output. Note that this output comes out with 2 values. So we have, first of all, this first part of the couple and this second part of the couple. The second part has to do with the indices, that is the positions of this top k values. So by default, as we saw, the k is equals 1. So by default we have k equals 1. So that's what we have by default. So if we run that, we should have the same answer. So that said, let's come slide this up. Okay, so what we're saying here is we going through each and every row. So we're going through each and every row. We look, what's the top value right here is 1. What's its position? 0. So we have 1 here, position 0. Top value is 100, position 2. Top value is 6, position 2. Top value is 8, position 2. So that's how we get these values. Now let's say we want to take top 2. Top 2, we see we have the top 2 values 1 and 0. We have their positions. 105 positions, 6 and 5. That's it. 8 and 3. As you can see, that's it. And by default, this is sorted, so you don't need to bother about sorting. Now you could change this to false in case you don't want to do, you don't want to have it necessarily sorted. Let's now go ahead and look at linear algebra operations. So here we have tf.linear. Go right here, we have tf.linear, and we have all these different linear algebra operations which come with TensorFlow. Let's look at the matrix multiplication given yours matmul. So tf.linear.matmul, what does it do? Multiplies a matrix A by a matrix B, producing A times B. Now note that this is different from the multiply, the TF.mat, the multiplier we had seen previously, as the TF.mat, the multiplier was an element-wise multiplication, whereas here we're working with a matrix multiplication. So right here, we paste this out. We have TF.linear.mat mul, and then let's go ahead and define these two matrices, x1 TF.constant, and then x2. So we have x2, we just recopy this, and then we have that. Now we have our x1, x2, and then we want to find the matrix multiplication of the two matrices. So we place here x1, and then we have x2. For now we have all this default values, so that's fine. Now let's run this and then see what we get. Now what do we have? We have an error, which is normal. We've been told that there is a mismatch. Now why is there this mismatch? If we check out the shapes, like if we print out the shapes of x1 and x2, x1, x2 shape, you'd see that both have shapes 2 by 3, 2 by 3. Now if you want to do matrix multiplication, then this isn't possible, since in order for matrix multiplication to be valid, the total number of columns we have here must match the number of rows we have here. So since this number of columns, which is equals 3, is different from this number of rows, it's not possible for us to carry out the matrix multiplication operation. So that said, let's modify this. Let's now have a 3 by 3 shaped matrix. So we would have this for that, and then we run it. See, that works. So this works now because this 3, that's the number of columns here, equals number of rows right here. Now let's even change this. Let's increase the number of columns. If we increase this number of columns, we have this. Oh, we'll increase the number of rows by doing this. So let's go back. Okay, let's increase the number of columns. To do that, we need to do this. 2, let's take 2, let's take 0. So let's run that. We see it's still valid because here we still have this equal this. That's the number of columns here equals number of rows here. So since it matches, we could still work that out. Now once you take off, so if we take this off, you see running this now, we still have the mismatch because here we have this 3 different from 1. Let's take one step back, rerun that, and that's what we have. Now also note that the output of this matrix multiplication has a shape which is dependent on its inputs. So if you notice, the output has a shape 2 by 4, and this 2 here is gotten from this number of rows, and then the 4 here is going from this number of columns. And that said, if now we instead have a 1 by 3, that is if we have 1 by 3 times 3 by 4, our output will be 1 by 4. So let's run this. You see you have 1 by 3, 3 by 4, our output is 1 by 4, and here's what we get. Now if you're not versed with this linear algebra terminologies, you could check on our linear algebra course available on our platform neurallearn.ai. So you could check on this. Here you will have this course on, or this section on matrix algebra. You would have matrix multiplication right here, and you get to understand all this in depth. So you could check on this preview. You see how here we explain step by step with some class exercises how all this works. Another way you could compute the matrix multiplication of the x1 and x2 is by having this. So we could say TF, or rather we could simply have x1 right here at x2. So this is matrix multiplication, while this is element-wise multiplication. So we have that at, run it, and we should have exactly the same answer we got here. So there we go, we have exactly this same answer. Another very common matrix operation is that of the matrix transpose. So yeah, we'll look at how to do the transpose of a matrix. Just put this dot capital T, you run that. Another way you could compute the matrix multiplication of the x1 and x2 is by simply doing x1 at x2. So you run this, you see we have exactly the same response we got from here. Now we move to another linear algebra operation or matrix operation, which is that of the matrix transpose. So let's compute the matrix transpose. We just have TF.transpose, and then we pass in our matrix. So we have passed in x1. We run that. You will notice that the rows becomes the columns, and you'll notice how rows become columns and columns become rows. So let's go back to our x1. Let's print out x1 side here. X1. There we go. We have this x1 right here. We see how the shape is 1 by 3 and that of the transpose is 3 by 1. It still contains exactly the same numbers, but now this matrix, that's the initial x1, has just one row. As you can see, one row, whereas here we have 3 rows. So this becomes this 2 becomes this 0 becomes this. Now let's take this now with x2. So we run x2, or rather let's print out x2 first. So we have x2 right here. Now notice how this 1 2 0, that's this first row, 1 2 0 2 becomes our first column. This second row becomes our second column, and this third row 4 5 6 0 becomes our third column. So we have it here 4 5 6 0. So this is basically the transpose operation. Now how is that related to this matrix multiplication? You may have noticed here we have transpose A false and transpose B false. So in the case you were trying to multiply x1 by say x2 transpose, you just have to put B true. Recall that x2 is B, so because initially we had A right here and B. So if we multiply this, or rather if we change this to true, now you'll be multiplying x1 by x2 transpose. Let's run this and we should have an error. This is normal. Why? Because we're multiplying x1 by x2 transpose. Now what is x2 transpose? Let us say we have tf.transpose x2. So that's the transpose, and then we get a shape. So we run that and we see that we have 1 by 3 times 4 by 3. We see that this 3 is not equals 4. So the number of columns here is not equals number of rows right here, and so we cannot do the matrix multiplication. So that set, that's not valid. So let's modify this. Let's say let's create x3. So we could have x3 which has 4 columns. So we could have x3 with 4 columns. Let's change this x3, and then yeah, let's say we have this just 2. Okay, so we have that. We'll print out x3. So we print out x3 shape, x3.shape. There we go. We run that. We have x1, x2, x3, x4. Now notice how sorry, this is x2. So this is x2 transpose. Now because this is 3 4 tends to 4 3, so it's normal. So we have x3. What we're trying to find here is x3 at x3 matrix multiplied by x2 transpose. So matrix multiplied by the transpose of x2. That's it. So let's print this out. Print it out and see if that's valid. So we have in this error tf.transpose. So there we go. We see that we are having an output right here, which is 2 by 3. That's because this 4 is the same as this 4, and then our output will take number of rows 2, and then this number of columns here 3. So that's it. So it kind of like takes this output, this outer axis that we have here. So that said, we have in our transpose of x2, and then we multiply x3 by 8. Now how do we have this exact same response without necessarily having to say for example TF the transpose x2, all we need to do is just specify that our x2 is going to be transposed, and here we have x3, so we have x3 and then x2. So it's just like we're multiplying x3 by x2, but we're saying that our x2 is going to be transposed. So that's it. We run that and we should have exactly the same response. So that's it. We have exactly the same response. Is doing this is the same as saying x3 times or x3 matrix multiplied by x2 transpose, since we're saying transpose B is true. Now if you send this to true, this should, let's check out what is going to be thrown. We are having x3 shape is 2 4, so if we have the transpose of x3 is going to give us 4 2 times the transpose of x2 is actually, let's check out x2 is actually 3 4, the transpose is 4 3, so we have 4 2 by 4 3. It's not going to work. So if we run this shouldn't work. We're having 4 2 by 4 3. Now if we change this, because we are having x2 transpose, let's say x2 transpose is 4 2, and then x3 transpose is 4 3. So for this to match, we must modify this. So if we change x3 to a 3 by 2 matrix, let's have that. Rather, yes, actually x3. So this x3 and this x2. So let's modify x2 such that we have a 3 by 2 matrix. And if we modify x2 to be a 3 by 2 matrix, then x2 transpose will be a 2 by 3 matrix. And if we have 2 right here, this matrix multiplication will match. So let's go ahead and change this into a 3 by 2 matrix. 3 rows and then 2. So let's take this off, take this off, take this off. That's fine. Okay, so x2 now is 3 by 2 and x2 transpose is 2 by 3. So this should match. Let's comment this out. That's fine. And we'll run it. So yeah, we're having an error. Okay, the error is coming from the fact that yeah, we need to put a transpose. So it needs to have TF.transpose, because now we're doing x3 transpose times x2 transpose. So we're gonna have this TF.transpose. Yeah, that's fine. So let's run it now and everything should work fine. See, we have exactly the same response because we're actually doing x3 transpose by x2 transpose, and this shapes here now match. Now the way we look at this next argument here, that's the adjoint, is exactly the same as with the transpose. An adjoint in a matrix is another operation which we will not get into the details, but just note that specifying this or saying that adjoint of A is true, for example, is the same as just saying we're taking the adjoint of x3 and multiplying by x2. If we say this is false and then here is true, so if we have this, then what we're saying is we're multiplying x3 by the adjoint of x2. So it's the same as or similar to the way we treat the transpose arguments right here. Let's now look at how to multiply matrices with greater than 2 dimensions. So let's go ahead and take this tensor 3D we had defined previously. We have tensor 3D right here. We just put it out down right here. We have tensor 3D. We've now defined this 2 3-dimension tensors, x1 and then x2. So there we go. We run this and this is what we get. So we have this 2 3-dimension tensors and we want to do matrix multiplication. So we could simply have tf.matmul or tf.linear algebra.matmul. We have that, and then we specify x1 and specify x2. Running this should produce an error. This is normal again because there is no matching in the shapes. Now, how do we look at this now? The way we look at this is quite straightforward. What we'll do is, when having this kinds of matrix multiplication where matrix multiplication is done in batches, what we do is we look at each and every batch and look at its corresponding batch in the other matrix and then do the matrix multiplication. So what we have here is we're multiplying this matrix here, this 2D matrix, by this matrix. Now, if you have to multiply this matrix here by this matrix, and then later on this matrix by this matrix, and then this matrix by this matrix, then you must make sure that there's a matching in their shapes. Now, this matrix right here is 2 by 3, and this is 2 by 3. We've seen already that 2 by 3 multiply with 2 by 3 wouldn't work because the number of columns here is 3 and the number of rows here is 2, which don't match. So what we need to do now is we could modify this tensor such that each of these matrices right here have a shape which will match with this, such that we could do the matrix multiplication. So let's change this now into 2 by 2 matrices. So instead of this, let's take this off, take that off, 2 by 2, comma, and finally here we have this, comma, and that's it. So now we have x1, which is 2 by 2, and then x2, which is 2 by 3. 2 by 2, 2 by 3 will output as 2 by 2, and then 2 by 3 will give us an output which is 2 by 3. So it's going to be 2 by 3 output. Now let's take that off and then run this. While we run that, we see this output. Let's take this off. Let's take this x1, x2 off. So we take that off, run it again so we could see clearly our output. Now notice how what goes on here is we have this matrix multiply with this, this with this, and so on and so forth. Now if you want to check this, let's go ahead and recreate this right here. So what we're gonna do now is we're gonna just take, let's take for example this middle values here off, take this off, take this off, there we go. We have this, okay, so that's fine. So now we have this, okay, we have this matrix, that's this 2D tensor, and then let's take this middle value because we chose the middles. So let's take this off, that off, and then yeah, we take this off. Okay, so we have x1 and x2, and then we're trying to print this out. We run this, we have 10, 20, 20, 11, 8, 6. So taking the middle values, if you look at this carefully, you see we have exactly the same response. So this confirms the fact that when we're doing what we call batch multiplications, where a batch is considered to be one of these indexes in the 0th axis. So we have this 0th axis right here. We have 3 indexes. So each and every one of those indexes is considered to be a batch. So when we're doing this kind of batch multiplications, we just take each and every one and multiply with its corresponding value in the other metrics. From here, we explain why we or how we use this sparse or this B is sparse and this A is bars arguments that we have right here. Now, the way this works is sometimes we have matrices which are full of zeros. So we may have a matrix like this. Let's modify this. And then here we have 0. Here we have a 0. Here we have a 0. And then here we could have a 0, 0, and that's it. So we could have matrices like this, which are made of mostly zeros. And so what happens is TensorFlow has a way of optimizing computations involving tensors which are mostly made of zeros. These types of tensors are known as sparse tensors. So when you specify that a particular tensor is sparse, TensorFlow takes that into consideration when carrying out the computation, and this helps us carry out computations even faster, since TensorFlow now knows that this matrix or the particular matrix or particular tensor is made of mostly zeros. So that's it. We could check on other methods like the adjoint method, which we spoke of previously. See this adjoint method right here. It permits you to get the adjoint of a matrix very easily. Let's now look at the band part method. In this band part method, we are actually rewriting the tensor but setting some values to 0 based on certain conditions. So here we have an input, we have a num lower and a num upper. We have the name as usual. So right here we have an input which could be of k dimensions as is defined right here, and then we have these conditions. So we have this indicator function which is say in band and with these conditions, and then we take this in band and multiply by the input matrix right here to finally get the output. So let's look at this example right here. We see that we have this input, we have this which is passed into the band part method, and then we have this output. You'll notice that this output looks similar to the input, but the difference is that at some positions you have zeros. So this -3 is 10 to 0, -2 10 to 0, and this -2 here 10 to 0. So that's how we look at it. Before looking at the special cases, let's take an example so we understand exactly how this works. Note that here this indicator function is defined such that for each and every element of this new matrix in band, because we're creating a new matrix in band such that each and every element is defined such that if this num lower is passed in here. So if, for example, like this num lower, if the num lower is less than 0, or m minus n happens to be the position of each element in the matrix or in the tensor. So if m minus n is less than num lower, less than 1, and if num upper is less than 0, or n minus m is less than or equals num upper, then this in band will be such that when multiplied with its corresponding element in the input, then that input remains the same. But if this condition is not verified, then that input turns to a 0. Here we have this tensor, this 2D tensor, which we've defined. We have that condition which was given to us in the documentation, and then what we do is we're going to define this two matrices. One is m minus n and the other one is n minus m. Notice how these two have exactly the same shape as the input. So what's going on right here? What happens here is we have m. First of all, you have to understand that m is for the rows and then n for the columns. So what goes on here is we have at this position we have the 0th row, 0th column. So m minus n, that's 0 minus 0 is equal to 0. At this position we are at the 0th row and the first
we are not allowed to use this multiple
times,
so we just have this
position 0th row minus second column, 0 minus
again,
2,
and we have our
this position.
So we have this
row,
0, -1,
0th column,
0,
1
2,
minus 0,
0,
1,
0,
yeah.
and finally 9,
second
32.
row,
This
or rather we had the all first row and the first column, so we have 1 minus 1, 0. Here we had the first
just
row, second column, 1 minus 2, -1, and then we continue with this and we get all these values. So this is how we get m minus n. We're simply taking the index, the row index minus the column index. Now we look at n minus m. For n minus m, we're looking at the column index minus the row index. So yeah, we have the 0th row, 0th column, 0 minus 0, 0. Here we have the first column and the 0th row. So 1 minus 0 is 1. Here we have the second column and the 0th row. So 2 minus 0 is 2. So that's how we get this n minus m matrix right here. Now, once we've got an m minus n matrix and n minus m matrix, we can now see how to get the output very easily. So we have this output. For now, we've replaced it by this axis, and we are gonna get for each and every element its exact value after going through this band part method right here. Since we have as input our lower to be 0 and our upper to be 0, we could take this condition off because our lower will never be less than 0. So we could take that off. So we could have this out. There we go. And now we'll be focusing on m minus n. So at this position, m minus n, which is 0, is actually less than or equal. It's actually equal the lower, since our lower is 0 and our upper is 0. So we have m minus n, here is it. It's actually less than or equals our lower. So we have that to be true. And then n minus m, which is 0, is actually less than or equals our upper, since our upper is 0. So that's true. So since all this is true, we have these value at this position. That's the 0th row, 0th column position. That's when m equals 0. This is where m equals 0 and n equals 0. So at this position where m equals 0 and n equals 0, this is going to be maintained. So this 1 is going to be maintained. So that's how we get this output, maintained. Now we move to this next one here. So in this next, we are having m to be equals 0 and then n moves to 1 while the first column. We come again and check here. M minus n, we have a -1. -1, is it less than or equals our lower? Yes, that's true. It's less than or equals 0. And then n minus m. N is 1, m is 0. That is 1. Is 1 less than or equals upper? No, that's not true. 1 is not less than or equals 0. So this condition is not fulfilled since this is not true. So both must be true. So since this is not true, this value, this -2, is turned to a 0. So here we have a 0. Now we move to the next. We do the same. Here we have a 0. Now what's sure is we're always going to have a 0, because if the 0 is maintained, we have a 0. If we turn to a 0, we still have a 0. So no need checking on this. Now we go to the next. We have 3. For this, we are at m equals, that's m equals 1, and then n equals 2. No, n equals, yeah, we at m equals 1, and then n equals 0, sorry. So we have n equals 0. Now we have n equals 0. We could compute this. M minus n. 1 minus 0 is 1, but 1 is not less than 0, or it's not less than or equals 0, so this is not true. So this 3 turns to a 0. So here we will have a 0. That's how we get the 0 right here. Now we go to this 5. We have m equals 1 and n equals 1. In this case, m minus n is equals 0, which is less than or equals 0. So this is true. This here is true. And then n minus m is 0. This is also true. So we maintain this value. So this turns to a 5. Wanting to get this, we have m equals 1 in this case, and then n equals 2. So we have 1 right here, and then we have 2. Okay, m minus n, we have 1 minus 2, -2. -2 is actually less than 0, so this is valid. And then here we have n minus m, 2 minus 1, 1. 1 is not less than 0, so this is not valid. That said, since this is not valid, this 100 turns to a 0. So that's it. You could just repeat this, and what you should have will be something like this. So here you should have 0, and then here you should maintain its value. And here you have 8, here you have 3, and then here you have 2. So that's how you get this. Oh, here you should have 0 actually. This is 0, here 0. Now everywhere, if you notice, everywhere m is different from n, you will never have a situation where m is different from n and then m is less than or equal 0, and at the same time n minus m is less than or equal 0. So that's why all the other values are 0 except for these diagonal values. So as you can see here, 1, 5, 6 are maintained. Now let's test this. So with this, comment that, and then we run this. So there we go. Here's the response we get. This comes to confirm what was said here, where the give this useful special cases, and we are told that whenever we have this 0, 0, that's we have an input with 0, 0, the output is going to be a diagonal matrix, so, or a diagonal tensor. So right here we understand why we should have that diagonal. Now if you repeat the same process, you should be able to see that 0, -1 we give upper triangular, and then -1, 0 we give the lower triangular. Now let's go ahead and see what this upper and lower triangular tensors mean. So yeah, let's take this to -1. We run that, and what do we notice? We notice that this matrix or the input, that's tensor 2D, does it here, is actually maintained. So 1, 3, 1, 2. See, everything is maintained except for the upper part. Now, if you have a matrix like this, and that you have this diagonal, and that all this is what we call the lower triangular part of the matrix, and this is the upper triangular part of the matrix. So as you could see here, this upper triangular part of this matrix is all zeros. And then if we take this to 0, so we have 0, -1. If you have 0, -1, and you run that, you'll notice now that it's instead the lower triangular part. So here we have this lower triangular part, right here, which is now made of all zeros. So that said, in case you want to get this lower triangular, you just have to specify 0, -1. Upper triangular, you have -1, 0. And then when you want to have a diagonal matrix, you just need to specify 0 on both sides. That's it for this band part method. We look at other methods. We have the color key decomposition. So yeah, we have a way of decomposing matrices. We wouldn't get into that. Yeah, we have the cross product. This is computed pairwise cross product of A and B. So yeah, you could compute a cross product of two input tensors. Yeah, you could get a determinant of a tensor. So we have an input, you could get its determinant. We have many other interesting methods here. We have the inverse, linarc.inf. We have here tf.linarc.inf, tensor 2D. We run this, we should have an error. So that's normal. So this is normal because to obtain the inverse of a matrix, that matrix must be a square matrix. That is, the number of rows must be equal to the number of columns. So that said, let's recopy this and then put it here. We redefine this tensor 2D, take this off, that's it. And then we now run this again. We told you could not find divide for node, and we given a set of data types which are registered for the operation matrix inverse. So this means most probably our data type isn't registered in this matrix inverse operation. Now we could search on Stack Overflow. We click on this. What we get here, I think your value should be float as error says. I have encountered the same problem while finding the determinant of a matrix and change the data type to float 32 and the problem is solved. So here we have a great way of checking for this kinds of errors, but nonetheless we understood already that this should most probably come from the data type we're working with. So let's change this to float 32 as it was set by the Stack Overflow user, and we have now this other error which corresponds with the error we expected. So here we are getting this error, and we told that let's take this off. We told that 4 different from 3. Now this is normal because, as we said, the number of rows must be equal the number of columns for us to find or calculate the inverse of that matrix or that tensor. So that said, what we're going to do here is, if we take this off and create a 3 by 3 matrix, what we have now will be the right answer. So we see we found the inverse of this matrix, and this inverse, so let's put this in a variable as a tensor 2D inverse. So this inverse is such that when you multiply, so let's run this, when you multiply tensor, or when you do a matrix multiplication, or actually not an element multiplication, or an element wise multiplication, when you do a matrix multiplication of this two, you should obtain the identity matrix. So here you have tensor 2D inverse, run that, and you see that you have the identity matrix. So here you have 1 0 0, this is 0, very small number, 1 0, this is 0 0 1. So here we have the identity matrix. Checking even in the documentation, you see that we're given a list of accepted data types, and the float 16 which we were using previously wasn't among. So you have to ensure that your input data types are in this list. We have this matrix transpose here, similar to the TF.transpose we had seen already. So that's our transpose. We'll see the matrix mul. That's it. We have the trace. We have the singular value decomposition of a matrix. So yeah, you could obtain the matrix's singular value decomposition. This returns three outputs: S, U, and V, where S is a tensor of singular values, U tensor of left singular vectors, V tensor of right singular vectors. So the SVD is a way of breaking up a matrix in a way that less important information contained in a matrix is eliminated. So that said, we could check this out. Right here we have SVD taking the tensor, so we could simply just pass in SVD and then get the outputs. So here we have SVD of tensor 2D, SVD of tensor 2D. There we go. SVD not defined, tf.linalog.svd. We run that and then we get this output. So we have these three outputs. Now let's define this SUV equals that, and then let's print out S. So print out S first to see the singular values. So there we go, we have the singular values. We print out U. We have tensor of left singular vectors, and then we print out V to give us our tensor of right singular vectors. So this is what we get right here. So feel free to always look at this documentation, and the more you use these methods, the less time you would even need to always come back to the documentation. So just make sure you keep practicing so you get to master all those methods. We now go ahead and look at the tf.ainsum method. In TensorFlow, you could have it as tf.ainsum. You could look at this documentation right here with some examples. Before diving deep into understanding how this operator works, it's important to know that this operator uses or takes in arrays of all sorts of dimensions, that is 1D arrays, 2D arrays, up to ND arrays. So we'll start straight up with this example with two-dimensional arrays, and we'll see how the ainsum operator can be used to replace the usual matrix multiplication. By matrix here, we're simply meaning a 2D array. In this example, we'll suppose that we have this array A and then this other array B. A is of dimension of shape 3x4, B of shape 4x5. In order for the matrix multiplication to be valid, we have to ensure that the number of columns of A have to be exactly the same as the number of rows of B. In that case, we have to ensure that generally this J has to be the same as this right here. And that's the case for this example. And so the matrix multiplication of A and B is valid, and multiplying this will give us C. But also note that the shape of C depends on that of A and B. As you could see here, if we kind of merge these two shapes and then take off this same shapes, that's this column for the first matrix and then this row for the second matrix, we would have 3x5. So we'll look at this outer values right here, this 3 and this 5, and that's what gives us the shape of the output matrix C. In general, if we have ij, jk, then we should have an output ik. So that's how we have this right here. It's very important for you to take note of the shapes whenever you're working with an ainsum operator. Okay, that's understood. Let's now dive into the code. We start by importing numpy as np. We have that, and then we have this two matrices A and B, which we've defined already. So let's comment this for now. We have the matrix A, which is on the slides, and we have the matrix B. As you could see, printing out this will give us A dot shape, and then we could print out B shape. So we have A dot shape, B dot shape gives us 3, 4, and then 4, 5. So it's 3x4 matrix, and then a 4x5 matrix right here as B. And that's it. Now let's look for the, or let's find the matrix multiplication of A and B. Note that in Numpy just suffices to have np the map mul. So this matrix multiplication, we pass in A and then B. So there we go, we run that, and we'll find this is the answer we get, which is correct. This is our C. So we've gotten our C. Now how can we replace this matrix multiplication with the AND sum operation? In order to do that, you just take note of this syntax right here. Notice how we have, first of all, this string right here. So we have the string, and what do we put in the string? First we have this ij, and then next we'll follow this ij. After the ij we have a comma, and then we have the jk, and then we have this arrow to ik. Now this can be read as A interacting with B to produce C. And the way we're choosing this ij, jk is such that it matches up with the shapes of A and B and with the kind of operation we are dealing with. Given that with a matrix multiplication we have A, so supposing it's ij, and then if we have a B, then we must ensure that the j we had here has to be the same as the j we have here. So this is just like the row. So I is the row, j the column, and here the row, and then here the column. So we have to make sure that the number of columns equal the number of rows. That's why you have this j and j right here. And then since the output is such that it takes the shape of the output is I, K, that's what we specify here. So we've taken A, B, and it's been transformed into a C. Now, whatever you have before this transformation has to be passed, obviously. So that's why we have this ij. So the comma here tells us that we have this ij matching up with A, and then this jk matches up with B. So we've kind of like separated the two different arrays to be passed. And then we have this IC, which is the output we get. That's why when we print this out now, we're going to have an output. So this IK is the output. We see clearly that this gives the same answer as just doing the matrix multiplication. Well, at this point, you may be doubting, like, why do I need to do all this when I could just simply put in the matrix multiplication or np.mul, AB, and then I have my answer? Well, that's a very common and normal question. And if you follow to the end, you'll see that in some examples or in many applications, you'd find that working with the AND sum operator is gonna be easier than working with the usual NumPy functions or methods you're used to working with. So let's go ahead. We've had that, and we now understand the AND sum syntax. Let's go ahead and look at many other examples. For our next example, we'll be using the AND sum operator to do an element-wise multiplication. Let's take this example right here. We have A, that's this matrix A, we have this matrix B. Obviously, for element-wise multiplication, we have to ensure that the two matrices A and B have the same shape. So as you could see from this, we print out A shape and B shape. We have 3 by 4 and then 3 by 4. Let's comment this for now. So we have this two right here, 3 by 4, 3 by 4. Let's go ahead to compute the element-wise multiplication, the Hadamard multiplication. We have that. There we go. We see that we have 2 times 2 gives us 4, 6 times 9, 54, and so on and so forth. So just simply each element on its position multiplying with its corresponding the corresponding element on the other matrix. Like if we just pick up this random, we have 4 times 5, 20. So that's the output here. Now in this case, you see that if we have this matrix A right here of shape ij, then B has to be of shape ij, and then the output has to be of shape ij. And so that's why you would see, let's comment this part right here. You would see that we have this input ij, or the first input ij, which is A, the second input ij, and then the output ij. So the AND sum operator automatically sees this as a Hadamard operation. So here we're gonna have the right output. Run that. Oh, let's take this off, and that's it. So there we go. We see that we have the same output as with the usual Hardeman operation or the usual element-wise multiplication. For our next, we go on to matrix transpose. So at this point, I'll urge you to like take a pause, try to come up with a corresponding matrix or the corresponding end-sum operation for the matrix transpose before continuing with the video. Now, hopefully you got it right. You have this matrix A right here, which is to be transposed. You see we have 2, 2, 1, 6, negative 2, 5, and so on and so forth. So basically we have a matrix which is of shape ij and it has an output ji. In this case, we would have, say, print the end-sum transpose of A is equals the print of np.end-sum. We have the np.end-sum of ij, which is being transformed to ji, and then we pass in the matrix A. So let's take this off right here and then run that. There we go. We have exactly the same answer. So here we pass in A, we have this ij, no need for any commas. That's if you have to multiply, let's say we have A, B, C, D, so on and so forth, then you have, say, ij, jk, k, l, l, m. Yeah, we have 4 right here, and that's it. So now we have just 1, so we have that. Let's take this off, run it again, that's fine. So hopefully you had this correct. We now move on to working with three-dimensional arrays. In machine learning, it's very common to have to deal with these types of arrays. Let's suppose we have this array A, which is a 3D array of shape 2 by 3 by 4. Now let's see the way we can read this. We have this whole array here, A, and then we have this 2 boxes in, this 2 arrays, this one and then this one. So that's where we have this 2 dimension right here. And now for each of this, that's for each of this arrays, we have a 2D array in it. That's for the first one, that's for this first box right here. We have this 2D array which is of shape 3, that's 1, 2, 3 by 4. And so that's why we have 2 and then by 3 by 4. So all this A is a 3-dimensional array of shape 2 by 3 by 4. We could generalize this as B by I by J. And then for B, we have a 2 by 4 by 5 dimensional array. Now, note that we have here that this B could be taken as a batch size. And this is because in general, many times in machine learning, computations are done on batches of data. So in this case, we could have this as a single batch. That's this box right here as a single batch. And then we have this other one as another batch, giving us 2 batches. So we have the batch size equal 2. And then we may want to do matrix multiplication or batch matrix multiplication, where we want to multiply this matrix right here of this 2D array with this one, and then get this corresponding output, and then multiply this one with this one, and then get this other corresponding output. And we may not want to, say, use a for loop to say for each of this we multiply this times this to get the output, and so on and so forth. We may just want to use a single operation which understands that this multiplication is done for every position in the batch. Also note that in these kinds of computations, the batch dimension remains exactly the same. We have here 2, 2, 2, while 3, 4 multiplied with 4, 5 gives 3, 5. So we still have this exact same value of B, which is maintained everywhere. Now that said, let's go straight away into the coding. We have this 3D array A right here, made of this 2 2D arrays, this other one, this one, and then this other 2D array. We could comment this part, and then we have to print out A that shape and then B that shape. There we go. Oh, print. And that's fine. So 2 by 3 by 4, 2 by 4 by 5. Now note that the matrix multiplication can permit us to do this without any problems. That is, we could get the we could do the batch multiplications with the NumPy's matrix multiplication, as NumPy's matrix multiplication understands that when data is placed in batches like this, all we need to do is to ensure that each element in the batch multiplies a corresponding element in the batch in the other array. Now, if we don't want to use this, we could also use the AND-sum operator. Now, the way we use the AND-sum operator here is by again specifying the shapes. So we have Bij for A, and then we have Bjk for B, and then for C we still have Bik. Notice how we have Ij, Jk, and Ik, while B remains the same. So with this, we'll run this, and we'll see that we have exactly the same answer for the two outputs. That's when we will use the matrix multiplication and when we use the AND-sum operator. And still up to this point, we see that we could always, or we may not necessarily use the AND-sum operator. Now, what if we want to sum up all the elements in a given array? So yeah, we'll look at another different way of applying or making use of this AND-sum operator. So here we have this matrix, or rather we have this 3D array A right here, and then we want to sum up all the values in that array. Here we have the sum, it gives us a value of 72. And then if we want to use the AND-sum operator, what we'll be doing is we have the shapes, that's Bij, we'll put an arrow, and then when you don't have any output, what you're simply doing is you're summing up all the different possible values. So that's what this signifies right here. So it's just like saying we're summing up all the possible values, and then we put in, or we make sure we have the right shape of A put right here. Notice that if we do this, you see we have an error. So we correct that, we have J, run that, and that's fine. We could also sum up all elements in a given dimension or given row or given column. Say we're working with a matrix. Here we're having this AND-sum. Let's just comment this. That's it. Uncomment this. Let's comment this part. Okay, so here we see that we have this matrix A, shape Ij, and now when we specify only one of this axis right here, what we're doing is we're summing up all the elements in each column, because the J is like the column. So this is the row, and then this is the column. So we're summing up all the elements in each column, and that's how we have this. We see we have 2 for the first column. We have 2 plus 2 plus 1, 5. 6 plus minus 2 plus 5, 9. 5 plus 2 plus 4, 11. 2 plus 3 plus 0, 5. So that's how we have that. So the way we understand this is we just summing up all the elements in each column. And then if we change this to I, we're summing up all the elements in each row. We'll run that. You see that for this row, we sum this, and then we sum that. Now moving to a more practical example, and this attention is all you need paper. You have this formula right here where we have the query multiplied with the transpose of a key. If this key has a shape of batch size by sequence length of the key by model size, and the query shape batch size by sequence length of the query by a model size, then we could define this NumPy array query of shape 32 by 64 by 512 and key 32 by 128 by 512. And then what we'll do now is define the query by transpose operation, where we would have MP, the AND-sum of this is considered to be, say, B, the batch size, by Q by M, and then this is considered to be, say, B by K by M. So here we would have B QM comma BKM, which outputs B. Now at this point we have to be very careful. We have QM times KM transpose, so this becomes BQM times BMK. And now when we multiply this QM and MK what you have is cure k. So here we have b cure k. Let's take it over again. We have b cure m and b k m. The batch dimension doesn't matter. We'll take that off. So we have this now. And then when we transpose this, we have mk. And when we multiply this, we're left with cure k. So that's how we have that. And then here we have as input cure and then k. So let's run this. And when there we go, we have this output, which is of shape. We could verify shape, which is of shape cure k. We have here cure, which is 64 by k, which is 128. So we have 32 by 64 by 128 output right here. Our next and final example will be inspired from the Reformer paper. In this paper, the authors explain how the data could be broken up into chunks and then they attend to each other. Again, you don't need to understand what's going on in that paper, but it's just for you to get an idea of where this problem well to present comes from. Now, supposing we have this matrix A of initial shape 2 by 4 by 8. Or to keep things simple, let's say 1 by 4 by 8. So we have a batch size of 1. We have a sequence length of 4 and a model size of 8. Here you could see this 1, that's the only single batch we have here. And then we have 4 rows and then 8 columns. B2 has a shape 1 by 4 by 4. So we have 4 rows and then 4 columns. And the paper we just saw, they further break up this data into buckets. So right here we have 4 different buckets. Now we see that this 8 columns are broken up into separate 4 by 2 matrices. Here we have the 4 by 2 matrices. We have 4 rows, 2 columns, 4 rows, 2 columns, and so on and so forth. Now the same is done for B, with the difference that we break this 4 up. That's we break the 4 columns up into 4 by 1 matrices, where we have 4 columns and just, or rather 4 rows and just 1 column. In the paper, there is a task which involves taking the transpose of this B and multiplying by A. And in doing that, we are in fact multiplying the corresponding batches and the corresponding buckets. So you see that again here we have some sort of 2 fixed dimensions, and then we have this dimension or this matrix here which is actually gonna be involved in the multiplication process. And so if we have A defined as BCIJ, or the shape BCIJ, and B BCIK, multiplying the transpose of B or getting the transpose of B will give us BC, say B and C fixed, and then IK turns to KI, and A is still BCIJ. Now we have KI times IJ giving us KJ, so we have BCKJ. So if we have this 1442 by 1441, we have 1412. And now with the Einstein operator, if we have the A given as this, here we have BCIJ and this BCIK. So let's just put it in comment. So we have this BCIJ, BCIK that we had seen already on the slides. Run that. And now we're trying to find B transpose by A. So what we're gonna have here is numpy sum of BCIK, because here we have B transpose times A. So we have BCIK comma BCIJ, which is gonna output BC. Now at this point, we recall that we're gonna have the IK, which is gonna be interchanged to give us KI. KI times IJ gives us KJ. So we're gonna have KJ just as we had in the slides, and then we pass in B and then pass in A. So we'll run that and then look at the shape. That's it. So we see that we're able to compute this very easily with an any-sum operator, as compared to the usual map mall where we have to ensure that the matrix B is transposed correctly. So here we're gonna have MP the transpose of B, and then we have to ensure that we have 0 1, so 0 1 fixed, and then we have 3 2, because this is where we do the transposing, and then we now pass in A from this. So we have that, and then there we go. we still have the same shape. We could take this off, then run this. You see that we have the same answer for both methods, but this method looks clearly is cleaner than this one, as if we have to go to say 5D array. We'll just, let's say for example we have 6 here, and then we have 6. All we need to do here is to say for example D, so we'll put that D that way, D, and that's fine. So let's run this again. See, let's put it in shape, and that's fine. But with this we would have to say 0, 1, 2, and then we would have to ensure that here we have 4, and then here we have 3 for that to work. And so this is an example showing how the AND-SUM operator comes to make our work clearer and easier to understand. Let's now look at the expand-DIMS method. With this method, we get to add an extra axis to an input tensor, and that extra axis has a length of 1. If we suppose we have this tensor, for example tensor 3D, then let's print out the shape 4 by 2 by 3. Now what we could do is we could add an extra axis such that this tensor 3D now takes a shape of 1 by 4 by 2 by 3. That said, what we do is tf.expand-dims, and then we pass in tensor 3D, that's it, and we specify the axis. So the axis specified to be 0. We're gonna have this output shape. So let's run that and then put out a shape here. So that's it. Now let's take a simpler example. Suppose we have x equals tf.constant, and then we have this right here 2, 3, 4, 5, for example. We could print out x, the shape, and then we could print out tf.expand-dims of x, and then we'll specify the axis to be 0. You will see that we're gonna have this shape 4, and then we have this output. Let's put this shape right here. We have this output 1 by 4. Notice how this tensor leaves from a 1D tensor into a 2D tensor. Still we have the same elements, but we've added one extra axis right here. This extra axis would have been added manually by doing this. So if we had done this, we would have had that extra axis. We run that. You see we have 1 by 4. And now doing the expand-dims, we have 1 by 1 by 4. So now we're left from 2D to 3D. And then if we keep doing this, you see how we'll leave again from 3D now to 4D. So we have 1 by 1 by 1 by 4. So that's how we look at the expand-dims method. If we want to do this expansion or this addition of this extra dimension in a different axis, we could specify that axis. Let's say the first axis equals 1. Notice how we leave from 4 to 3 now to 4, 1 to 3. So we kind of like fit in this here. Let's take this off. We kind of like fit in this here. So when you say axis equals 0, it's fitted right here. Axis equals 1 is fitted here. Axis equals 2 be fitted here. Axis equals 3 fitted here. Axis equals 4 invalid. So that's it. Let's take axis equals 4 for example. You see it's not valid. You have 3. You see now you have 4 by 2 by 3 by 1. From here we look at another method which is like the opposite of this expand-dims method. Here we have the squeeze method. With the squeeze method, what you have is you're taking this input, specify the axis, just like similar to the expand-dims method, but here we instead remove the dimension of size 1 from the shape of the tensor. So let's get back to this. We had run this and we had let's take this to x squeezed. Let's define x squeezed. Sorry, x expanded. X expanded is this. Let's run that. We have x expanded 1 by 1 by 1 by 4. Now let's do x squeeze. X squeezed is equals tf.squeeze, and then we pass in x expanded. So firstly, we're going to specify the axis to be equal 0, and then we print out our x squeeze. So we have x squeeze right here, x squeezed. Print this out, and we should have this 1 by 1 by 4. So one axis has been taken off. Let's do this several times. So here we have for I in range. See, let's do this twice. Copy this, paste this out here. There we go. X squeezed, x squeezed. So we start by squeezing the first time, and then we continue squeezing. Let's print out x squeezed here. So here we have x squeezed. That's it. We run that, and we should get this. So there we go. We've left from this 4D tensor to this 1D tensor. Coming back to this other example where we had the shape, that is, we had expanded such that this extra axis was added on the last position. So here, what we're gonna do is do a tf.squeeze with the x which has been expanded, and then specify the axis. So now we're gonna specify the third axis because we want to squeeze out this third or last axis right here. Now before squeezing out that last axis, let's suppose we're trying to squeeze out this zeroth axis. You see, we cannot squeeze out this because we expect the dimension or the length of this to be equals 1 before we could squeeze it. So that said, if we specify now 3, you see that works fine. So now we have 4 by 2 by 3. Recall that this was exp that shape was actually 4 by 2 by 3 by 1. So squeezing out now, this works now because we specified the right axis, which is of length 1. So that said, we've looked at the squeeze and the expand dims methods, which have to do with modifying or reshaping tensors. Let's look at the reshape method. So here we have our reshape method. As usual, we have the definition, reshapes a tensor, and then we have some examples. So right here, we'll see how we're modifying or reshaping this 2 by 2 tensor into a 1D tensor. Before looking at that example, let's take a look at how we could use the tf.reshape to modify the shape of this x expanded, that is this x which produces the shape, such that we have an output of 4 by 2 by 3. So there we go. We have this, we pass in x expanded, and then we specify the shape we want to get as output, or the new shape of our tensor. So here we specify 4 by 2 by 3. We don't want to get a tensor, so let's put that shape. Even here, let's take this shape, we run that, and this is what we get. We see that we have exactly the same output shape right here. Now let's change this, remove this, and then we compare these two tensors, and we see we have exactly the same outputs. So this tells us that what we did with the squeezing could be possibly done with the reshaping. Now let's take another example. Supposing we have this tensor x reshape, we could actually reshape this. That is, we could have tf.reshape and then pass in x reshape, such that we modify it or we change it into a 1D array, so, or a 1D tensor. So if we put this to say 6, we run that, we should have an error. So invalid syntax. Well, this is different from the error we expected. Okay, so this is the exact error we get. To input to reshape is a tensor with 8 values, but the requested shape has 6. So that said, the fact that you could reshape doesn't mean you would just be able to modify any tensor and then change that to just any type of shape. You have to make sure that when reshaping, the number of values that you get in the initial tensor actually fit in this new shape or this new form you want this tensor to take. So here we have 8 values, and you don't expect to reshape this into 6 values, so you have to put this to 8. So running that now, you see how we've reshaped this, and we have 3566, 3566, and then 46, -1, 2. So it's kind of like we've flattened out this matrix. Now let's do another, taking a look at another reshaping. We could change this to 4. So here we have 4 by 2. Now we're changing, this 2 by 4. This is already 2 by 4, so we could put this to 4 by 2. 4 by 2. We run that. So yeah, we have 2 by 4. Now we could change this to 4 by 2. Notice that this actually isn't exactly the same as the transpose of this matrix. So reshaping it from 2 4 to 4 2 doesn't get the transpose of this initial tensor x reshape. We could change this again. Let's say we have 4 2 4 2 1. We run that. See that works just fine. And this is because with this we expect 8 values, and here we have this 8 values. Now it may happen that you will be dealing with tensors wherein you don't exactly know whether this is a 4 by 2 tensor you want to get as the output of this reshaping. So you could just put a -1, and TensorFlow automatically knows that this is 2. So if you run this, you'll get this output right here. Let's print this out. Let's have this printed out. So we print this out, copy this, print it out. We have 2. We run it, and we see that we have exactly the same output. Now if you just put in -1, yeah, you would expect to get the same output as this. So put in this, you see it automatically understands that the value you should have here should be 8. We now look at the concatenate function, that's tf.concat, which permits us concatenate tensors along one dimension. So right here we have this values as input, we have a specified axis, and then we have the name. So at the bottom here you can have this values, which could be a list of tensors or just a single tensor. Now let's look at this example. So let's just copy this example from here. So we're going to copy this example. We paste this out right here. We have T1, T2, and then let's look at the output or get the output of this. Before getting to the output, we're going to have print T. This is actually a list. So let's say print tf.constant T1.shape, and then we print tf.constant T2.shape. So we have that. So we're printing out this two, T1 and T2, and then we're concatenating them. Let's run this. We have the shape 2 by 3, 2 by 3, and we have this concatenation, which is 4 by 3. Now what do we notice? We notice that this first part here, this first two rows are actually T1, and the next last two rows are T2. Now the reason why we have this is because we'll specify this axis right here to be equal 0. Now saying our axis equals 0 simply means we're doing concatenation across the rows. Doing row concatenation means we're taking this we're taking this first tensor, taking this other tensor, and then we are completing the rows of this T1 right here. So it's just like we were taking, let's copy this. So this concatenation operation is just like this. We're having this here, completing like this, and there we go. So this is exactly what we're doing. We actually just completing this and then having this. So that's why here when you look at this, you see it's exactly the same as what we have here. So that's how the concatenation operation is done. Let's go back. We have T2, T1. Now we could modify this and take to 1. Now if you specify the axis to be equals 1, it means we're doing concatenation across the rows, or rather across the columns. So that said, instead of adding extra rows as we just did previously where the axis was 0, now we're adding extra columns. So we come here and we add extra columns. So here we have 7, we have 8, we have 9, and then here we have 10, we have 11, and then we have 12. So that's what we're gonna get. Let's go back, take that back, that's fine, and then let's run this and see what we get. We see that we have 1 2 3 7 8 9, so we add the extra columns, and then 10 11 12. So with the axis equals 1, that's when we were specifying that we were working on the columns, we add in extra columns. When axis equals 0, that's with the rows, we add in extra rows. Now what if we're having 3D tensors, or let's say we're having a 3D list right here. Let's take this, add that, and then add this. You'll look at you will know the shape we'll get from here. So this is going to print out the shapes, and then let's specify this to 0. So we run that, and then we have 1, 2, 3. So shape 1 by 2 by 3, 1 by 2 by 3, and then our output here is 2 by 2 by 3. So in fact, we're doing the concatenation on the zeroth axis, which is this axis right here. So our output is 1 plus 1. Now we'll go back slightly. So let's get back to what we had previously. There's a point we didn't mention, so let's run this again. We had this. Now what we forgot to mention was that the output, that is when we specify axis equals 1, our output will be, we go to the axis 1 and then we add this 2 up. So our output will be 2. So we fix the other axis and then we add this 2 up. So we have 2 by 6. Now when it's 0, we're going to fix this other axis and then we're going to add this one up to make 4 by 3. So let's run this and we get 4 by 3. Let's go forward. We will run this again, and this is what we have. So as we're saying, since we specify axis 0, we fix the remaining axis and then we add this up. So here we have 2 by 2 by 3. Now what if we specify the axis to be equals 1? If our axis equals 1, our output should be fixing, we fix the 1 and then we add this 2 up, 1 by 4 by 3. So saying we're concatenating on the first axis here means we'll be stacking up the rows and we'll get this kind of output. So let's run this. There we go. We have 1 by 4 by 3, and then we have this here, which is this, and then this other one, which is the T2. If we had to do this for axis 2, we would have this as expected. See, we just stack this up on the columns, added this extra columns, and then here we added this other extra columns right here to obtain this new tensor we have now. Another very commonly used method in TensorFlow is the stack method. That's tf.stack, tf.stack, and then here we just go straight away, and then you see the kind of output it produces. So here we have we specify axis equals 0. It's kind of like similar syntax with the concatenate. So we specify axis equals 0. We run that, and then we should have this. So there we go. We have, instead of like with the concatenation where we just join these two tensors across the rows, here when we specify axis equals 0, it simply means we are creating a new axis. So if both tensors are all 2 by 3, 2 by 3, like this, we create a new axis, and now in the new axis, depending on the number of tensors we have. So if we had, for example, if we have to add T1 again, let's add this T1. Depending on the number of tensors we have, we are going to have this shape, or rather we're going to have this axis having a length corresponding to the number of tensors we have. So like here we have this 3. So that's why here we have 3. If we take this back to 2, we're going to have 2. So basically, we actually stacking up this tensors, and you should be able to clearly see the difference between the stack and the concatenate. And then using this new T1, T2 for the stack, we have that when we have the stack axis equals 0, there's the output we get, shape 2 by 4 by 3. So from here we could understand that we have T1 4 3, T2 4 3, and then we create this extra axis at the 0th position. So we create this extra axis right here. So 4 3 4 3. Now we add this extra axis and we have now 2 4 3, where basically this T1 and T2 stay intact. As you could see here, we have this is T1 and then this is T2. All the values are intact, forming this big tensor of shape 2 by 4 by 3. So we leave from this 2D tensors to this 3D tensor by just stacking up these two tensors. Now when we change the axis, or when we're working with axis equal 1, the stacking up is done such that we having this 4 3 4 3, but the outputs we get is such that this additional axis is at the position 1. So unlike here where this additional axis was at the position 2, now this additional axis is at the position 1. So it's just like we having, let's say we having 4 and then we having 3. So if axis equals 0, we add it at this position. If axis equals 1, we add it at this position. If axis equals 2, we add it at this position. We also understand that if we have 3 of this, so if we have, let's say T1, and then here we take T1, let's run this 2. If we run this 2, this is what we now obtain. We have here, for when axis equals 0, we have 3 by 4 by 3. So let's see why we have this. We're having this 2, or we're having 4 by 3 stacked with 4 by 3 and then stacked again with 4 by 3. So we have this 3 tensors being stacked here, T1, T2, and then T1 again. So here we're gonna add an extra axis, but then since we have 3 of this, we have with this extra axis 3, length 3, so we have 3 by 4 by 3. That's why we have this right here. And then for when axis equals 1, we add that extra axis. So we add that extra axis. Here we have 4 by 3. We add the extra axis in the middle. So here we have 3. So that's why we have 4 by 3 by 3. Let's check this out. We have 4 by 3 by 3. When the axis equals 1, the stacking is done at this position 1 here. And so what you have here is this 1, 2, 3 stacked with 7, 8, 9, and again stacked with 1, 2, 3. This is because we have T1, T2, T1. So if I take this off, if I run this, I have 1, 2, 3 stacked with 7, 8, 9. So I have this 1, 2, 3 here stacked with 7, 8, 9. And then to obtain the next, I have 4, 5, 6 stacked with 10, 11, 12. I have this 4, 5, 6 stacked with 10, 11, 12. And then the next is 5, 6, 2 stacked with 0, 0, 2. 5, 6, 2 stacked with 0, 0, 2. 1, 2, 1 stacked with negative 1, 5, 2. That's it. 1, 2, 1 stacked with negative 1, 5, 2. So let's go back to when we had T1 right here. T1, we run that, and that's it. So we understand exactly why we have this responses here. We understand exactly why we have this output right here. To get this, for example, we have 562 stacked with 0, 0, 2 and restacked with 562 since we have T1, T2, T1. Now at this point, you could pause the video and try to find the output when we have axis equal 2. When axis equal 2, we are meant to have this. So let's just recopy this, paste that. When axis equals 2, we have 4, 3, 4, 3, 4, 3. That's T1, T2, T1. And then 4, 3. And then we add this axis at the end. So here we have still 4, 3, 3. Now to make it clearer, let's just take T1, T2. So if we have T1, T2, here we just have this 2. So in this case, we just have 2. Now we have 2, we're gonna have 4, 3, 2. So 4, 3, 2, and that's it. So we have 4, 3, 2, unlike here where we have 4, 2, 3, and here where we have 2, 4, 3. That's if we're considering that we're dealing with just T1 and T2. So that's it. Take that, and that's fine. So as we could see, our output now will be 4 by 3 by 2, and the stacking will be done on the columns. So let's look at what we'll get. Let's have this run right here. Let's run this, and then we compare with our values here. We see we have 4, 3, 2, and then this output can be seen as you taking this row, that's this first row, stacking up with this one, and then transposing it. So it's kind of like similar to what we had here, 1, 2, 3, 7, 8, 9, but here we now transpose it. Then here we have 4, 5, 6, 10, 11, 12, transpose. To obtain this, we transpose this. To obtain 1, negative 1, 2, 5, 1, 2, we transpose this. Either you look at it that way, or you could see directly that you have 1, 7, there we go. next 2 8, there we go, next 3 9, here is it, and then we move to the next where we have 4 10, so we have 4 10, 5 11, 6 12, and so on and so forth. So that's how we get this output right here. In the documentation, we see how the stack method can be written as the concatenation here. That's can be written as a combination of the concatenation method and the expand dims method. So here we have the stack of T1 T2 on 0th axis, which produce this, and then following the exact same method we've been given in the documentation, we have this concatenation, and then we run it. So we run this and we see that we have exactly the same answer. The reason why we have exactly the same answer here is simple. You see that we have this expand dims. So if we have, let's suppose that we have this two tensor, or we have this list made of T1 and T2, which are the tensors we want to stack. So here we have 4 by 3, and then we have 4 by 3. Obviously, when we do expand dims of each and every one of this, that's basically what we're doing here for all this. When we do this expand dims, 0th axis, we'll be left with 1. So we've added this extra axis, we're left with this. Now, once we do this, we now concatenate on the 0th axis, and we have the output 2 4 3. That's because we just basically add this 2 up. So 1 plus 1 gives us 2, as we saw with concatenation. So here we have 2 4 3, and this coincides with just doing a stacking of these two tensors T1 and T2. Then we get to the method path, that's tf.path right here. We have the definition, and then we have this example. So we just look at this example. Here we have this tensor T, and then we define this patterns, which we've seen up here. So we have to pass in the tensor and the patterns, coupled with the mode and its constant values. Okay, by default this is 0 and here is constant, but we must put in the tensor and this patterns. Now let's take a look at that. As we said, we have the tensor, we have this patterns, which itself is also another tensor, and the way it works is we are going to pad this tensor right here with a constant value. By default, this constant value is 0, so we're gonna do the pattern with a value of 0. That's why if you notice, you have this 1 2 3. Here is it here, 1 2 3 4 5 6. This is it, and then we do this pattern with all values surrounding it being zeros. Let's copy this and check this out in the notebook. We run this here. Okay, so that's what we get. Now let's modify this and say we want to have constant values to be equal, say 3. We run that, and what do we notice? We notice that we still have 1 2 3 4 5 6, but all the remaining values surrounding it are actually all 3. Now we are having this output here, but how is this output generated? Now if you look at this carefully, let's send this back to a 0. If you look at this carefully, the way this tensor is defined, that this patterns tensor is defined, is such that here we have the number of rows above the initial tensor. That's if we have this initial tensor here, we have a certain number of rows above this initial tensor, which we are going to pad with this value 0. So here we have 1 row above, 1 row below. So that's why you notice here, let's run this. You see we have this. That's why you notice here we have this 1 row above, 1 row below, and then we have 2 columns to the left. That's these 2 columns, and then 2 columns to the right. So that's how we generate this padded tensor right here. Now let's modify this. Let's say we want to have 3 to the right. If we want to have 3 to the right, you see here we have now 3 to the right, still 2 to the left, 1 row above and 1 row below. So that's it. Now let's change this. Let's say we want to have 5 rows below. You see we have 1 2 3 4 5 6, and then all these 5 rows below. Now we could change this method to reflect or symmetric as we've seen here. Another way of doing tensor indexing is by using this gather method, which comes as tf.gather. Yeah, as usual, we have the definition and some examples to permit us understand exactly how this works. So that said, let's look at this first example where we see how this tf.gather does a similar thing as the usual indexing, which we've seen already. So right here we have this tensor, which we see here, and then we have the tensor that's params 3 simply means we're selecting the value or the element at the third position, third index. So if we count here, we have 0, 1, 2, 3. This is our third index, and the output should be P3. So right here you see we have P3. Now if we want to do this same thing with the gather method, we just have to pass in our params and then specify the index. So you see here specify 3, and then we have this output. Now let's space this out here. Unlike with the indexing where we had, for example, supposing we want to do params or want to take in these values, what we're going to do is just pass in, say, 0, because yeah, this is actually 0, 1. So 1, 2, 3. So if we want to take all these numbers, we'll have 1, 2, 3, and then we add a foot. So here we have 1, 2, 3 plus 1 to give us those values. So here we're gonna have P1, P2, P3. That's it. P1. Oh, we started from 0, so we start from 1. So we have P1, P2, P3, which gives us this as expected. Now if we want to redo this with the gather, we have this. We pass in the params, and then we specify this indices. So right here we have 1, 2, and 3. We run that, and that's fine. We have P1, P2, P3. We could also do TF the range 1 up to 4. So we have that. That's fine. We run that. There we go. We have exactly the same response. So let's get one step back. We have this. So let's play around with the syntax. Now, supposing we do not want to get maybe this 3 consecutive elements or any k consecutive elements. Supposing we want to get this 0th element, we want to get the last element, and want to get this element right here. So this is 0, 1, 2, 3, 4, 5. I want to get 0. That's 0, 1, 2, 3. So I want to get 0. I want to get this last, and I want to get it second to the last. So that said, I'll just have to put here 0. I want to get the last element, so -1, and then so that 1, -3. So I run that. I expect to have those elements. You see here we have an error. So this gather method doesn't understand the syntax. So we just have to use the usual syntax. Here we have 0, 1, 2, 3, 4, 5. So we'll put in here 5, and then here we have 3. We run that again. There we go. We have P0, P5, and P3. You see that this permits us to do this kinds of even more complex tensor slicing. Let's take another example. We have, supposing we have this tensor right here, params, and then we want to have tf.gather. We pass in params, and then we have 3, 1, for example. Now note that this params is it's a 4 by 3 tensor, so it's of shape 4 by 3. So we want to gather this 3, 1. So good, look at this again. Let's even start from something simple. So let's start from just 0. You see that doing this will get us 0, 1, 2. So yeah, we're saying that we want to get just the first, or rather just the 0th element, and it happens to be this one right here. Now this other params here, we had the shape params that shape. We had a shape of 6, and then here we having a different shape. So this is 1D, and this other params here is 2D. So the way we approach the indexing here is slightly different. Now let's look at this. When we do this gather, we have the index 0 selected and the default axis is equal 0. Even here our default axis was equal 0. That is with this one right here, the default axis here is equal 0. If you do this, you will still have exactly the same response. Oh yeah, we should run this and run that. So you see that we have exactly the same response. Now let's get back to this. Our axis is 0, means that we are dealing with this axis right here, which happens to be the columns, or rather which happens to be the rows. So putting out 0 here simply means we're working with the 0th row. So we're working with this, and that's why the output is as such. Now if we do this, that's if we do 0, for example, let's say 3, and we run this, what we get is 0, 1, 2, and 30, 31, 32. So we get in this and we get in this. This is because we're dealing with the 0th row and the 3rd row. So 0, 1, 2, 3, we have this and we have this. If instead we want to do this selections based on the columns, then we will have to deal with the first axis. So axis equal 1. Running this is what we obtain. Here we're saying we're dealing with a 0th column. So we have 0, 10, 20, 30. So that's it right here. And then the 3rd column. But here we don't have any 3rd column. So that's why it just by default just places all these zeros right here. Now let's change this and put, for example, the 2nd column. We have 2, 12, 22, 32, 2, 12, 22, 32. We could change this to 0. We run that and we have 2, 12, 22, 32, 0, 10, 20, 30. Now let's modify this. Let's modify our params. So let's have this. Yeah, we add this and we run it again. Before running that, let's go back to 0. So let's suppose the axis is 0. Our shape is 1 by 4 by 3. Now our axis is 0, so we are on this 0th axis right here. And if you considering the 0th axis, here we have only this. So we basically have only this. Now we're saying we want the 2nd. So we want the 2nd element of this 3D tensor, but there is no 2nd element since we only have just this one. So what happens is we have all the zeros right here. Now the next is we say we want the 0th element. Since the 0th element actually exists, we see what we get now is exactly this. So it's basically giving us back this here. Now we turn this to 1. What are we supposed to get? Since here we are on this axis, we're focusing on these rows. We pick out the 2nd row. So 0, 1, 2, we pick out the 2nd row and the 0th row. So let's run this and we expect to get 20, 21, 22 and 0, 1, 2. So let's run that. There we go, 20, 21, 22, 0, 1, 2, which is what we expected to get. Now let's double this. So let's have this. Supposing we have this type of 3D tensor, let's modify, say this one. Let's modify that. 0, 0, 2, and that's it. So let's run this now, and what do we get? We see that since we are on this, we've picked out the first axis. Let's even go back to 0. Let's run this. Here we see again that we still have the 0, 0 because there is no 2nd element. But if we had 1 right here, if we had 1, yeah, we don't have the zeros anymore. We have this here. Here is it, and then we have the 0th, and here is it. Yeah. Now let's put this back to 2 and then send this axis to 1. We run that, and here's what we get. So as we are saying, we're working with this axis. This one fixed, we're working with this axis. We just function with the rows. So for this element right here, we check out the rows. What is the second row? This is the second row, and this one. So that's what we have here. And then for the next element, where the second row, we have 0, 5, 55 and 3, 1, 21. So that's how we obtain these. Now we have this other method, gather ND. So it's slightly different from the gather. What it does is it gathers slices from params into a tensor with shape specified by the indices. So this indices is gonna influence the output shape. So you have to say, whereas in tf.gather, that when you're working with the gather method, indices defines the slices into the first dimension of params, and the tf.gather nd, indices define slices into the first n dimensions of params. That said, let's look at some examples. So right here we have some examples. Here we have this indices, the params, gather nd, which takes in the params and the indices. Note that unlike with a gather, here we don't have this axis argument. So the gather nd doesn't take in the axis argument, and we just basically have this params and then the indices. So let's see how this works. We have a param, this tensor right here, or this list, which would subsequently become a tensor after getting to this method. And then, as it was said in the documentation, we're gonna have a tensor which is gonna get the shape of the indices right here. But the way it's gonna get this is such that we're gonna have this zeroth element of params, and that zero element of params happens to be this. Here's the zeroth element of params, and then here we're gonna have the first element of params. So this happens to be this. So let's run this, and we'll see what that gives us. We have here A, B, C, D. So that's fine. We have exactly the same as params. Now, if we take this off, so let's run that, we would have A, B. We have this 1/2 shaped output. Here we have this A, B right here. Notice how, since we've picked out the zeroth element, we have this is actually the zeroth element. So we take this and then we replace right here, and we get this output. Let's modify this to take E and then F. So here we have EF. That's it. Let's do 2, for example. We run this and we should get EF. So that's it. We have EF. Now let's do 2 with 1. So 2, 1. What do we have? We have F. Now why do we have F? We have F here because we're picking up the second row, that's 0, 1, 2, this row and the first column. So that's why we have just this F right here. This is different from the gather, where when we do this, that's when we have like this index is specified 2, 1, and then let's run this, and then we do tf.gather params indices here. Yeah, we should have this here EF, that's 2, and then CD 1. So we should note that with this gather ND, our output shape is defined by this indices right here. So what we have is 2, 1. We pick this up, and then there we go. Here's what we have. Whereas with a gather, first of all, we have an axis which is 0. So we're working on the 0th axis. That is, we're working with all the rows, and then we're picking out the second row and the 0th, or rather on the first row. So that's why we have EFCD. Let's take this off. We take this other example here. Now we have this indices, so obviously we know that our output is gonna take the shape, so we expect to have this kind of output. But then what values are we gonna put in this output? So that's what we're gonna look now. We have this here 0, 1. since this is a 3D shaped or it's a 3D tensor, we have 0. When we say 0, we're picking up this first element here, the 0th element. And when we say 1, we're picking up this element right here. Now 0, 1 means we're picking up this element, and then 1 means we're picking up this, because first of all, when you pick up this element, you have 2 elements in this element. So we have this here and we have this here. So when we pick up this element, that's the 0th element right here, we now have to pick up this first element, or the element on the first position. So here we have the 0th position, and then we have the first position. So that's how we have C0, D0. Now for this other one right here, so we already know that we will have an output which will look like this. So we will have C0, D0. It's actually strings, so we understand that. Yeah, we have 1, 0. Now 1 here means we, after these 2 elements, we have out of this 1 and this element right here, we're picking out this 1. So we pick this 1 here, and then after picking this 1, we're gonna pick out the 0th element. So we have in 2 elements, this 0th and this first element. We pick out this 1. So we have A1, B1. So right here we should have A1 and B1. Now let's run this, and we confirm that we have exactly the values we expected. Now if after picking, for example here, if we pick this 0th element and then we pick the first element, so we've picked the 0th and then we've picked this first element right here. Now what if we want to pick, that's if we pick this first element, in this element we have 2 elements, that's C0 and D0. What if we want to pick this 0th element? So if we pick the 0th element, we should have C0. And now here we've picked this first element, we've picked the 0th, that's A1, B1. What if we pick the first element, that's B1? So pick this one right here, we run that, we should have C0 and B1. So that's it. Let's take this as an example. If we have this indices given to us, and then we have the params, and we're trying to get the we're trying to get the output right here. Now what we would have as output, as usual, would be of similar shape with the indices. Now we have 0, 1. So notice how we're having here a 3-dimensional indices. So we should have something like this, 3D. There we go. We have this, and then we have this. Okay, so we have this 3D indices. Now we pick out 0, 1. Picking out 0, 1 simply means we're picking out the 0th element, and then after picking out the 0th element, we pick out this first position here. So we have C0, D0, and then from here, so we first of all start by picking out C0, D0, C0, D0, and then we have the next 1, 0, 1, 0. We're picking out this first element, and we're picking out A1, B1. So we have this A1, B1. That's it. We're done with this first part, so we close that. So we have this here. We have this 2D tensor right here, which is like this one, and then we move on. So for the next, we have 0, 0, 1, 1. Now 0, 0 is simply this. So we have the 0, and then we have this 0. So we have A. Let's just copy this. We have A right here. We have A1, B1, A1, B1, and then 1, 1. That's picking out this 1, and then this 1. So we have C1, D1, C1, D1. That's it. Okay, so we're done with that. We could now take this off. So that's fine. Let's now go ahead and run this and compare our answers. Here we have, as expected, this 2 by 2 by 2. That's because we have this 2 elements, and then for each of these elements we have 2 by 2 tensor. So that's normal for the shape. And then here we have C0, D0, A1, B1, A0, B0, C1, D1. We actually having something different here. Here we have A0, B0, and here we have A1, B1. Let's understand why we should have A0, B0 right here. We get back to this. At this position, we have this 0, 0. Now, 0, 0, we have the zeroth element, and after picking up the zeroth element, we have this zeroth position, A0, B0. So that should be A0, B0. So that's normal. We made an error here. We should have had A0, B0. We now look at this gather ND method while taking into consideration this argument. That's the batch dims argument right here. By default, the batch dims equals 0. So by default, we have this output right here, where to obtain this 0, 1, when you say 0, 1, you're simply saying you're taking the 0th element, and then with the 0th element, you're taking the first index. So you have this C0, D0, and then 1, 0 means you're taking this first position and 0. So first position, and this first position, you have this 0th position. So A1, B1, and that's how we get this. Now, let's turn this batch dimension to 1. You see that we have a different output. Now, let's understand how this output is gotten. You have to note that this batch dims here is kind of like making this method to be batch aware. So that said, once we have this indices passed in, that's this indices here, we understand that this corresponds to a given batch. That's this batch, and this corresponds to this other batch. So that said, we are having 0, 1, and then we have already picked this batch. So when we select the batch dims equal 1, here we've already picked this 0th batch. And so doing a 0 here means we're picking this 0th element here, and then doing a 1 means after picking the 0th element, we're picking this 1 here at position 1. So that's why we have a B0. Now for the next, as we said, is batch aware, so this matches with this second element here, with this element at position 1. Now 1 here is 1, and 0 here is 0, C1. So that's how we obtain this right here, unlike with the former where we had batch dims equals 0. Let's look at this other example. We have this indices, we have the params. Now when the batch dims equals 0, saying that you want to have 0, 1 is just like picking this. So we pick this, and then we have 1, which is C0, D0. So that's why we have this C0, D0, 1, 0. We're picking this element at position 1, and then 0 is A1, B1. So C0, D0, A1, B1, and then A0, B0, C1, D1. We've seen this already. Now, when you say batch dims equal 1, what you're saying here is all the indexing you will do here will match with this 0th element. So this 0th element here will match with this. So it's now batch aware, and then this first element will match with this. That said, 0, 1 here means first of all, we've already selected this. So 0 means we're picking out this 0th element, and then 1 means we're picking out this 1. So we're gonna have B0. So we have B0, 1, 0. We've already picked this one. So we have we have this 1, 0 will be this, and this. So we have B0, C0. Now for the next, we have is batch aware. So we've already picked this, and then 0 is this. 0, 0 is picking only this one. So we have A1. Now for the next 1, 1 means we're picking this one, and then we're picking this D1. So we have B0, C0, A1, D1. Now let's run this, and we hope to get an exact answer. So here we have C0, B0, C0 as expected, and then A1, D1. You could continue exploring other methods. We'll now move on to racked tensors. So we have here tf.racked. We have this overview. We'll try to understand first of all what racked tensors are about. To understand the racked tensors, let's take this example. We have this tensor 2D. You could print out this shape, tensor 2D shape. We have that, which is 4 by 3. Now let's copy this and then paste it out here and modify this one. So we'll modify this. So we have this 3, this like this, 2, 3, and that's it. Now let's print out tensor 2D. Let's print out tensor 2D. There we go. We'll print out the shape. What we get here is an expected error. Can't convert non-rectangular Python sequence to a tensor. So as you could see here, tensors are meant to be rectangular. That is, if we decide to have 4 rows, like in this case we have 4 rows, that's this, and this, then each of those 4 rows must have the same number of columns. So here we have 3 columns, this one column, this 3 columns, this 2 columns. Hence, this error is thrown here. But then it happens that sometimes we may be working with data which comes in this form. That is, we may have data where we could have, for example, this rows, or we have this row having 3 columns and this other row having 1 column, this other row even having, say, 5 columns. We could have this kind of data. And the way TensorFlow deals with this is by using racked tensors. Now let's see how to create a racked tensor. To create a racked tensor is quite easy. We have tensor, let's say tensor racked is equals tf.racked.constant. So instead of just tf.constant, we have tf.racked.constant, and there we go. So we could also have this as like a simple list. So we could have this as a list. Let's put it this way. We could have a list and then just pass this in here. So we have tensor 2D. Now let's go ahead and print out a shape. We have tensor racked. That's it. Let's run that. We have an invalid syntax here. Okay, it's because of this. So let's run this again. And there we go. We see we have 4 by none. Now 4 because we have 4 rows, that's fixed. But then we don't have an exact number of columns, so we just have a known here, meaning we don't know exactly the number of columns we're dealing with. But nonetheless, we have a racked tensor which we've just created. So we see here we have this tf.racked tensor. Unlike with this, let's print out tensor 2D. If you print out tensor 2D, you see you have tf.constant. Now this is actually a list, so let's say tf.constant, and then we have that. Oh, we have an error here. Let's use this. That error is because it's not rectangular, so that's normal. So okay, there we go. We see we have tf.tensor here, and then here we have, let's run this again. Here we have tf.racked tensor. So this is an example of a racked tensor, wherein we have non-rectangular data, like in this case here. Apart from this constant method which we just saw, we also have methods like the Boolean mask. Now with a Boolean mask, we pass in our tensor or our list, and then we pass in a mask. Let's check out on some examples. So we see here we have this 1, 2, 3, 4, 5, 6, 7, 8, 9. We pass in a mask: true, false, 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 and true, false, false. notice how wherever we have the false, this data or this element in the data is taken off. So this 2 is taken off and we're left with 1, 3. So that's why we have 1, 3 right here, because we have true, true. And then here we have all false, so this is an empty list. Here we have true, false, false, so we left with just 7. So that's it. And from this, we form this racked tensor right here. Now, we could also do this for rows. So instead of just specifying for each and every element, we just say true, false, true, and then this understands automatically that this means our first row is going to be left out. So it's, or rather our first row is going to be taken. So we have 1, 2, 3 maintained. And then this next is false, so it's going to be taken off. And then this next is true. You could check on these other methods. We are going to look at the tf.racked tensor. This racked tensor class contains several methods, as we could see here. Let's check on this from row length method right here to see how we could create racked tensors. It takes a potentially racked tensor. The row lengths are specified, the name, and then validate. So let's see how this works. We have this input right here, and then we have this row length specified. So we run this. What do we get? We have 3141 empty list, 5926 empty list. Now how has this gotten? You see that with this row length, we're saying, okay, we are going to start from this first position or from the 0th position, and then the first 4 or the next 4 we have will form a row. So we have 3141 forming this row, and then from here we say the next we're gonna have is gonna be an empty list, or the next row we're gonna have is gonna be empty. So that's why we have this. And then from here we continue from our position where we go to the next 3. So we've gone to the next 4 at this point. We created this empty, and then now we're going to the next 3, 592. That's how we have this. And then from here we have the next 1, 6, and then we have an empty. So if we take this empty off, or if we take that 0 off, you see you don't have the empty list anymore. So that's it. That's how we can create this racked tensors from the row lengths. From that, we will now look at the from row limits method. Here again, we have this input values. We have the row limits. Let's see how that works. Here, since we're given the row limits, we have this first value 4. So we come and put ourselves at this position right here. We simply go 1, 2, 3, 4 elements. We fix ourselves at this position. We create this first element of our racked tensor. There we go. And then for the next 4, we are still at that same position. So we move, we're still at that same position. Since we are at that same position and that we've already used up this first 4 positions, we have this empty list. Again, we move to the 7th position. So we go, let's go this way. We move to the 7th position. Here we are. At this point, we pick this up. So here we have 592. And then from the 7th position, we move to the 8th position. So we go to this position right here. We pick this up. We have the 6. Again, we have this 8th position. We're still at the same position. Since we've already taken off all of this, we just have an empty list. So that's how this works. Let's now take one last. You could always come back to the documentation to explore all those other methods. With the from row splits method, what we do is we're actually checking out in this row splits we've been given here each element and the next element. So we have 0 to 4. See right here, 0 to 4. We pick out this 0 to 4. And here we're considering that this position here is 0, this position here is 1, this position here is 2, this position here is 3, and then this position here is 4. So when we say 0 to 4, we're actually taking from this 0, 1, 2, 3, 4. So we fit ourselves at this position and we get this first 4 elements. That's how we get 3, 1, 4, 1. And then the next, we're still at 4. So we're still at this position. So we've already gotten this 3, 1, 4, 1. So we just have an empty list here. Now we move to, we have 4 to 7. So we go again from here. This is 4, this is 5, this is 6, this is 7. So we have all this 5, 9, 2. And then we have 7 to 8. We have the 7, and then here we have 8. So we get 6. And then 8 to 8, since we are the same position, we have this empty list right here. We could also convert tensors directly into sparse tensors using the from tensor method. So here we have this tensor defined. It says rectangular, and then we could automatically convert this into a sparse, or rather into a rect tensor. This from tensor method takes in this length parameter, where with this length given to us, we're able to take only certain parts of our rect tensor. So yeah, since we have 1, it means for the first row, or for this row that we have here, we're gonna take only this one, or the first element. The next, we're gonna take no element, so we have an empty list. The next, we're gonna take all 3 elements, so we have 6, 0, 0. So that's it for the rect tensor. You can always explore all the sort of methods in the documentation. It should be noted that many times we will have to deal with data which contains many zeros. And a more efficient way of treating and storing these kinds of data is by using sparse tensors. So we get to tf.sparse right here. Click on sparse tensor. There we go. We see how to create the sparse tensors right here. We specify the indices. We're gonna understand this soon. So let's say we have 1, 1. It's actually 2D. So yeah, we have 1, 1. Yeah, we could have, say, 3, 4. There we go. And then we specify the values this is gonna take. Let's say we want to have 11 and then 56. We specify the shape. Let's say it's 5 by 6. There we go. We have indices, values, and dense shape. So yeah, we've defined this tensor sparse. We've run it, and then let's print this out. So yeah, we have tensor sparse. There we go. We see that we have exactly the same values we put out here. But then let's understand how this relates to a usual tensor, or how we could map this to a tensor. Now, to do this, let's do tf.sparse.toDense. So note that we are not doing tf.sparse.sparse tensor, we're just doing tf.sparse.toDense directly. So we take this and we pass in tensor sparse. We run that, and what do we get? We have this 5 by 6 tensor right here, which happens to be what we had defined here. So we had defined the shape to be 5 by 6. We said that at the position 1, 1, that's at this is the 0th row, the first row. So we have this position, first row, first column, 1, 1. We want to fit in this value 11. And we also said that at the position 3, 4, want to fit in the value 56. So we go 1, 2, 3. That's 0, 1, 2, 3, and then 0, 1, 2, 3, 4. So this is a position 3, 4 right here, and then we put in this value 56. So that's how we're able to map this back to a usual tensor. Then you will notice that all the remaining values are zeros. So the sparse tensors permit us to work with these kinds of tensors more efficiently. This last tensor type we'll be looking at is the string tensors. So here we have tf.strings, and then we have these different methods which we could use. Before looking at those methods, let's see how to create a simple string tensor. So right here we have tensor string, call it tensor string, equals tf.constant. So basically we're just having a list made of string elements. So hello, I am a string. So that's it. Let's print this out. We have tensor string. We run that, and there we go. We have this string tensor right here, which has been defined, d type string. and then we have the different elements which make up our string. You have, as we have seen previously, all these string methods right here. Let's look at this join method. With this join method, we are able to combine several elements of this list together and with a specific separator. By default, our separator is this empty string right here. So that said, let's do this. Let's say we want to have all these elements joined together. So we'll just have tf.strings.join, and then we pass in tensor string. So we pass in tensor string. Our separator is equals, let's say for now, let's keep it at its default value. We run that, and what do we get? We have hello, I am a string. Now let's suppose that we want to have a separator, which is the space. So let's have this separator. You see hello, now there's some space between. Now let's modify the separator. We put a plus, and we run that, and there we go. Hello, I am a string with this separator right here. We have other methods like the length. The length basically tells us how long our string is. So here, in the case where we have this, you see you have hello TensorFlow, and you have this Unicode string. You see how we're able to get that this length is 5, 1, 2, 3, 4, 5. This is 10, and then this is 4. We have the lower method, which converts all uppercase characters into your respective lowercase replacements. We have the ngrams method, and all these other methods which you could explore. So that's it for tensors. We now move on to variables. To better understand tensor variables, let's come back to this model which we had defined at the beginning of this course. These values a1, a2, b1, b2, which are given initial values, get updated as we train our model. And so we need to use variables which can be updated as we do model training. That said, instead of using the tf.constant, we are going to have xvar, which is equals tf.variable. So this is how we define this, and a variable must always be initialized. So here we pass in x, and then we print out xvar, and there we go. We have this tf.variable, its name, shape, data type, and its content. We could include this. So let's say we want to have var1. Let's specify that as name. So we have that, and now we've specified the variable's name var1. Here's how we create a TensorFlow variable. Notice also that we have this trainable argument right here, which says whether during the training we update that variable or not. And so if this is false, then during training this variable wouldn't be updated. If it's true, then this variable can be updated during training. And then we have this other arguments which you could explore. Now this tf.variable has other methods. So we have the assign method, for example, and we'll see an example of how this is used. We have this variable defined, so we pass in this number 1, and then we assign its value to 2. So now when you print out this v, what you're gonna get is this new value for our variable. Now you see we have the assign add, this other method right here. With the assign add, we're simply doing addition on the elements in our variable. So let's check on assign sub, this assign subtract. Here we're just doing subtraction. So here we have xvar, and we could do some subtraction. So we say xvar.assign sub of this 3, 4. So it takes in this 3, 4, and then what goes on here is we're gonna have 1. That's the actual value of xvar. No, xvar is actually this. So okay, yes, 1. So xvar, we have this 1 minus this 3, and then this 2 minus this 4. So let's run this. What do we get? We have xvar -2, -2. If we modify this to 6, we have -5, -8. Reason being that the first time we did the update, we went to -2. We had -2, -2. Now we're doing the subtraction. So we have a -2 minus 3, -5, and then -2 minus 6, -8. So now we have -5, -8. Let's go ahead and add 8. So let's just do this. We have add, we run that, we should have 0, 0. So that's fine. We have 0, 0 because -5, -8 plus 5, 8 will give us 0. So as usual, you could check up on all these other methods in the documentation. Then another important point which we need to mention is the fact that you could decide on what device you want your variable to be. So generally we have CPUs, GPUs, TPUs. Let's check on this runtime. Let's change runtime type. You see that presently we're using the GPU. So if we say none, then that's the CPU, TPU, and then let's do that. So here we could have with tf.device, and then we specify that device. In this case, we have GPU. So we have that GPU. With this, we could define our xvar. So you define your xvar in this scope, and you are actually saying that you want your xvar. So xvar, that's variable. We want our xvar to be in this GPU. Now, if you want it to be in a CPU, you just simply specify your CPU, and that's it. Now, you could also let's print this out first. So we have xvar. Let's run that, and then you could check out the device which is found. So check out the device. You see this is now CPU. If we modify this to GPU, we run that. It's in the GPU. You should also note that this could be done with just simple tensors. So we could have x tensor tf.constant and then 0.2. There we go. Print out x tensor dot device. So let's run that, and we see we have this. Now we could, let's do this, copy that. There we go. We have now, let's put here CPU. So we have the CPU, and then let's take this off. There we go. We run that and we compare. So here we have a GPU, and then we have a CPU for our tensor. That said, it's possible to initialize. So we could initialize this right here like this. Let's say we want to have 1, 2, 3, 4. So we want to have 1, 3, 4. That's our x. Let's say this is x1, and then here we want to have x2, which is tf constant, and then we want to have here 1. So let's say we have this here. Let's put that as list. So we want to have this x1 and x2, which is in the CPU, initialized in the CPU, and then we want to carry out the computations in the GPU so that these computations could run faster. So right here, what we're going to do is we're going to have x3, which is equals x1 plus x2. So as simple as that. Now, obviously, broadcasting will happen here, and then we're going to have 1, 1, 1, which when we add with all this, it gives us 2, 4, and then 5. So that's it. Let's now print out our x1. Let's take this off. Let's print out x1. Let's print out x1 and where it's found. So x1 the device, copy that, take this off. That's it. We have now x1, x2, rather x3, here x3. So let's run this and see what we get. We see we have this CPU, and then here GPU. Now we have 2, 4, 5 as our output, which is expected. So that's it. We've just looked at TensorFlow variables, and this marks the end of this part on tensors and variables. Don't forget to like and subscribe so you never miss amazing content like this. And in case you want to gain some solid foundation on linear algebra, you could check out our course. See you next time.